Hi, my name's Bob Grinier and I'm a volunteer with the Martin Fleischmann Memorial Project, so thank you for patiently waiting for me this evening. I believe I've got most of the slides I want done for you. Can I just have a shout from anyone that can confirm that they can hear me, because that would be great, before I start talking to myself. And we are going to be talking about the before and after, the calcium carbonate versus HHO, and I'm calling this silver linings, and there's a very good reason for that, and we will work through this. Hi Artifact, hi P900 Cool Picks, hi Slobodan, great to have you here. I think you're going to enjoy this one. Hi Henk, hi Corky, hi Ron, it's great to have you all here. Okay, I don't know why I'm not seeing the beginning part of the chat. Maybe I can see it on my other computer if I switch to that. I want to call you out if you're in the room. Obviously, if at any point we have like hundreds of viewers, then possibly then I might avoid doing that. But for now, I'll call you out. So I think I've got some stream people. Hi Anne, hi Gordon. It's great to have you. Hi guys. Okay, all right. So let's get to this. Okay, so I'm going to just kill a few things that are a little resource heavy on my other machine here, like Photoshop, if I'm not using it at the minute, and then we'll get going. Okay, so, and I don't need the stream on that one as well. Good. Okay. Right. See if this is going to die on me. Okay, right, so back in the room with the presentation, and it is here. Great, you can hear everything. Good. Okay, so this is about Fukushima, and I'm going to go over some little background for those that haven't been following this series. Hopefully it will be enough so that you know where we're coming from. But essentially, in 2017, I realized that the most likely thing you can do with what I was then understanding to be exotic vacuum objects and the like, equivalent to ball lightning or micro ball lightning, was to actually destroy matter. But it would appear that one of the things it does like that is basically reorganizing it, and it's averaging it. So if you get some light elements and some heavy elements, it finds something in the middle. But what it tends not to do, and this is true for all low energy nuclear reactions, is it doesn't produce any radioactive elements unless either it's pushed too far. You have certain interactions that cause a normal kinetic interaction, like the emitted protons interacting with vanadium-50 and producing a neutron that way in a standard sort of kinetic nuclear reaction, or the tritium, which is observed, which is the one thing that LENR tends to be able to produce given the right circumstances. And the interesting thing is, that's the thing that we want to get rid of here. And why am I saying that? Well, because at Fukushima there is a 1.25 trillion tons. Trillion? I don't think so. 1.25 million tons. That would be bad if it was trillion. Million tons of tritium-laced water. And this isn't actually water that's completely tritium, like TTO. It could be a little bit of a HTO or DTO or TTO. But most of it will likely be HHO, and some of it will be HDO. But the majority of it is still HHO, or H2O as we commonly drink it, hopefully. And and we want to keep it that way. So if we go to our presentation here, I walked through this in a previous presentation, and this was discussions on the triated water treatment for Fukushima Daiichi nuclear power station. And you can go and look at this document, which was published on the 12th of May 2020 at bit.ly/3ILOJH7, and we looked at that before, but since we started this series, it was actually found that earlier in the year, despite them doing a call for September to come up with other solutions, they'd kind of already decided, the Japanese, that they were going to probably move ahead with the plan to build a tunnel and dilute the wastewater and then dump it into the sea. And the reason is you build the tunnels, you want to keep it away from the inland fishing waters. So the previous idea, I don't think it necessarily, the one that's included in here, I don't think it necessarily included this building of a tunnel, but the one that's listed in here is about 30 million, whether or not the tunnel was there. And they were going to use seawater, mix it with the tritium-laced water and dump it out to sea. And I would like to see this avoided, and I would like to see this avoided by potentially coming up with this argument where we can generate energy, generate light with this tritium-laced water and turn it into a resource that can be valuable. And I'm just going to go over my phenomenological hypothesis, which I've talked about before, and highlight just a few points that are relevant to this presentation, and also with some of the learning that we've had in recent weeks. So essentially what I'm saying is the process of what I'm calling now coherent nuclear transmutation and ball lightning, or just straight coherent nuclear transmutation, but saying and ball lightning is giving a nod to the natural phenomenon that I believe underpins this entire process. And given the fact that the Russians have, for the best part of 30 years, called this cold nuclear transmutation and ball lightning, I think they're pretty much on the money. Anyway, the process likes to fit things into a small box. I've used this phrase because it's very, very easy to understand. Although, as I clarified in the previous presentation and at other times, I don't really mean a small box. When you say box, people think that the box is, you know, it's got an X, Y, and Z, or a height, depth, and length. Obviously, if you are wanting to fit anything into the smallest surface area, i.e. the maximum volume of stuff into the smallest surface area, that would naturally be a box, which is a sphere. And over here, you can see what I suggesting, given the evidence we have at the moment, is this iron crenellated sphere. This one is from Vega, but we've seen them in various other systems, including from natural ball lightning. And this is a sphere, and the reason it's a sphere is because that is the minimum surface area that holds the maximum volume, that relationship. And so the box in my head is not a height, length, width. It is a radius and, you know, of a sphere. Basically, it's a spherical box, if you can imagine that. And that's essentially what that box is in my mind referring to, although this is just an easier thing to conceptually talk about. And so therefore the energetically advantageous product will be favored. And what I mean by that is that if you compress things into a smaller space-time, that does less distortion of the space-time, and that gives you energy out. And that doesn't actually matter whether you are talking about a chemical reaction or a nuclear reaction or a subnuclear reaction. Whatever organizes the matter into a smaller volume does less distortion of space-time, and that is where your energy gain is coming from. I'm going to skip a few things here, but I'm just going to draw out this. Products are largely alpha conjugate nuclei, including alphas, with carbon, oxygen, silicon, and calcium. This one I've highlighted here. And very, very many experiments have found calcium, and we're going to show a few examples there. And if you actually look at the Earth's crust, you've got oxygen at the top here, which is the most abundant, then silicon. Silicon dioxide is quartz, and that's a lot of what rock is. And then aluminium comes here as the third most abundant element, and then the next one is iron. So iron, the fourth most abundant element in the crust, and the first most abundant element in the crust is what these iron-rich cores, I believe, of at the moment, subject to any data that refutes it, is the core of ball lightning. And so it's right up there. Now, the next one after that is calcium. And, you know, you can get to calcium readily by taking various combinations of things, which I will talk about. Now, how do you crush... Before I go on to that, the other thing is that I want to draw your attention to here is production of protons and tritium due to fermionic nuclei. Other fermionic nuclei, for example, are favoured 23 sodium, 27 aluminium. Here we go. And sodium here. Here we go. 61 nickel, which I observed in the SynthesTech analysis in Sochi when I was there, of the Hutchison MFMP sample 18 coral twist, and the 207 PB, which is these are both fermionic isotopes, and they were both on what would appear to be the synthesized elements on these flux loops on the coral twist sample. And I believe 61 nickel was also observed in a higher concentration in Savatomova's corona discharge experiment that she shared at ICCF 23. And I believe she might have also seen this as well, I can't remember. But anyway, as they don't easily fit into a small box condensate. So if you've got a condensate which is mostly alpha conjugate nuclei or bosons, i.e. integer spin, they can all occupy the same space-time, or composite nucleons or composite particles where they have a integer spin. But if there's something that's kind of like the odd one out, it gets kicked out. And so that's what I'm suggesting is there. So that is my phenomenological hypothesis for coherent nuclear transmutation at this point. It may change. But how would you get things into a very small box? So we're seeing something that's in a small box, but what is pushing it into this very small box? Well, I had this presentation that I started producing a couple of years ago, but I never finished it. But I've pulled out a couple of slides for it. And I called it Crushing Matter. And I'm just going to start by saying these are some typical magnetic field strengths, which I've taken from this reference you can see down at the bottom here. And I put my mugshot up there. Hello. And so a neuron depolarization. So if you wanted to get someone's brain and you wanted to depolarize it, then you only need 0.5 of picotesla. The Earth's magnetic field comes in at just 550 microteslas. A refrigerator magnet, 5 milliteslas. A junkyard electromagnet, the sort you might imagine lifting up a car and throwing it into one of those crushers, is about 1 Tesla. A clinical MRI scanner is about 0.5 to 3 Tesla. And these are the sort of thing where they, see what's going on in your body and your brain and stuff by putting some sort of contrasting material in there. And when you go and have an MRI scanner, as I had the pleasure of having one twice, once last year after I felt a bit wonky after my sniffles infection, and then there was another time when I was in ICCF 22 in 2019 and I got severe gout, and I went in and had an MRI on my hip at that point. And what they tell you when you go in for an MRI, you may or may not know this, is to remove every metal item you can possibly think of from your self. And the reason being is that this strength is enough to rip those things off you and potentially damage the machine and hurt yourself. And so just at the kind of 0.5 to 3 Tesla field, you're getting that kind of action. Now, research MRI scanners are coming in at 7 Tesla to 11.7 Tesla. And this is the kind of range, I think, that or certainly laboratory NMR spectrometers, these are the kind of range that they're talking about where MIT, I think, have just upped their magnets. Then largest pulsed field created in a lab non-destructively. So 97 Tesla, you can get a much, much higher intensity of a magnetic field when you have a pulsed field. Okay, and then largest pulse field created in the lab destroying equipment, but not the lab, which I think is quite nice, at 730 Tesla. Okay, well, I have the second slide here, and it's referring to a couple of key points that I think are very important here with regards to the exotic vacuum objects, which are microball lightning, even according to Ken Shoulders. And so these are the key points here. And that is that the magnetic fields at 9.2 kiloamps, and this is the amount of current that he says is flowing around, I think it was a 20 micron torus quanta of what he calls condensed plasmoids, as a nod to Bostic, but I believe exotic vacuum objects is a more accurate term. But anyway, that's what he calls them, condensed plasmoids. And the torus ring current is up to 50 million Tesla. 50 million Tesla. So over here, the highest that's been achieved on Earth, at least in this table and from this source, is 730 Tesla in a pulse. This is 50 million Tesla. That's a lot of Teslas. Okay, so the magnetic pressure in the condensed plasmoids, EVOs, can exceed 2 times 10 to the 21 pascals, which is 5 orders of magnitude higher than in the solar core. So this is a pressure that is 5 orders. So that's like not 10, that's not 100, that's not 1,000, that's not 10,000. that's like 100,000 times more pressure than you have in the center of our sun. Okay? And he then goes on to say that is results in nuclei density in the range of pulsars, which is a form of a neutron star. So you can imagine that if you had this level of pressure, that you are going to get some, well, essentially if it's a form of neutron star, then the matter is being crushed to a point where the electrons and the protons are tending to produce neutrons. And that may be important as we move forward in this presentation. Due to the intrinsic current of a condensed plasmoid, they will exhibit pseudo-ferromagnetic behavior, even at high temperatures. Pseudo-ferromagnetic behavior, even at high temperatures. Well, I'm arguing that probably with these little things in the middle, you know, it's not surprising they have all kinds of magnetic behavior. And then I have this conclusion phrase here that basic exotic vacuum objects, that you can think of them as intense magnetic vices. So these things can crush matter in the torus, potentially in the core, and I believe that they can cluster, and we've seen this in the work of Bogdanovich, and that according to Bogdanovich, at the Moscow Nuclear Physics Institute, is the equivalent of ball lightning. And I think he's probably right, because what it looks like is the itonic mesh, the cage that we have observed on Amasa vibrator plates, and it would seem in the inside of these hollow structures in the copper in the experiment of Vega by Henk. So thank you, Henk, for that. And so here we have it. And one might ask, you know, how they can be stable. Well, this is from a presentation I gave in 2017, but it's actually from a 2007 document by David Yerth, who was using high-density charge clusters, which is the phrase that he was using for exotic vacuum objects across 11 years to remediate radioactive emissions, i.e. remove the emissions rate from spent nuclear fuel. So he was firing these exotic vacuum objects into nuclear radioactive targets, and they were deactivating, you might like to think of it. So this is just a slide from there. So then it comes to the fact that what was the proposal that we were talking about? Well, I'm going to run over the rough proposal. Then I'm going to I'm going to do a live reaction calculator using the nanosoft.co.nz reaction calculator to show the premise behind the idea. And then I'm going to talk a lot about calcium and to flesh out why I suggested calcium would be the way to go. So first off, the overall here is that in 2012, Amasa showed using Fukushima tritium water that he could remediate something like 2 half-lives in 1 month just with the vibration. And we've shown that the vibration, I think pretty conclusively, using the coherence that occurs at the figure of 8 nodal pairs, you can do transmutation. And since tritium really doesn't want to stay tritium when it's got a chance to transmute in these coherent matter situations, then it is not surprising that he was able to do that remediation to 2 half-lives within 1 month. And it is a real shame, because that was 2012, and you could argue if that had been implemented then, potentially much, although it's a slower method, potentially much of the radioactivity in this water could have been dealt with already by now. Anyway, so we need to go a little bit faster. So vibration and electrolysis, we've talked about how oxygen may be key to the production of the special heavy gas in the kind of oxyhydrogen HHO systems. and that the a Mars vibrator system does that. And so this produces high quality gas. A Marsa is one, but there are others that have some sort of vibration in there, either by design or by luck. And the other thing is that whilst it's a low efficiency relatively to what you can get, it's robust in that because it's vibrating and the plates are quite far apart and so forth, its efficiency doesn't change that much, and it's extremely simple to both maintain and build at scale. Vibration alone may assist in the stabilization, so I've talked about that, especially with additive after concentration. So you could add salts into the water where that might have a advantageous transmutation, where the tritium would like to react with the additive, and therefore not only could you use that to accelerate the process of the transmutation, you might even be able to produce something of value out of that, and maybe we could have an idea of what that might be by the end of this presentation. But there are many potential options. Anyway, so burning gas in a mode to force coherence. So what I argued was, if we are burning against a block, if you're gonna get this coherence, it's kind of causing some electron bunching. Just like in the Solin patents, the calcium oxide that is formed, it has a very low vapor pressure. It can go to a very high temperature without turning to a gas. Let's put it like that. And so this promotes the formation, in my view, of the coherent matter, and also the light that's involved and so forth. And then also Ken Shoulders talked about going through a hole, and that would force some turbulence, which would lead to the formation of toruses, which could pinch and promote the overall process. And if in these steps the transmutation occurs, then your work is done. If it's only partially transmuted, you can recycle, because what happens is your electrolyzed water becomes water again, and then you run it through again, and potentially it's then done after just a number of these electrolyzed burn cycles. And then if it does not transmute, it can easily use heat for vapor release. And so one of the methods that they were suggesting was to produce heat to create vapor and then release the vapor, or you could release the water gas directly. In that case, you could either electrolyze it more standardly when it's at a very low concentration, and release the hydrogen, which go up into the upper atmosphere with relative isotopes. Okay, so we're going to now do the reactions with hydrogen isotopes with calcium. The reason I've chosen calcium, I will delve into in more detail. It's just I happen to drop this slide in here. It's not the best place for it, but there it is. Okay, so yeah, Gordon, same temperature does help get to coherence, and the important thing is that if you have a lot of material, a lot of bunching of energetic things into a confined space, then the degrees of freedom go down, and so the more likelihood it is of cohering. And so that is the hypothesis behind that. And if you want to kind of understand this, just go and look at in remoteview.icu, where I talked about the 2001 suggestion, where Matsumoto is suggesting getting a linear accelerator to produce protons at exactly the same energy, and they would come out, and then you would fire an free electron laser with bunched electrons at this proton beam coming out, and it would spontaneously form itonic clusters, which are microball lightning. And so you kind of think of it a bit like that, and there may be a process going on in this where the oxygen is removed from the water, in HHO gas rather, in the same way that I believe it's being taken away in tungsten from Irving Lanier in the 1909 onwards, and in other experiments where you have tungsten or titanium or something that readily oxidizes. For instance, aluminium that was used by Yul Brown in the 1980s and 90s to remediate nuclear waste. The aluminium is grabbing the oxygen out of the HHO, leaving a lot of protons. The protons have a little dipole. They stick to the magnet. The overall temperature rises to a point at which you exceed the Curie point of the ion, and then instantaneously all this atomic hydrogen comes off, all at exactly the same energy, exactly the same temperature, because the Curie point is a very precise thing. I will detail this in much more detail, but then they come off and they form the itonic clusters. So basically that's essentially the equivalent of what was being suggested by Matsumoto, but without having to have a linear accelerator and without having to have a free electron laser. So a little bit simpler. Anyway, moving on, I will do a whole presentation on that whole subject, so it's extremely clear what I've just said. I have kind of talked around it in the past. So we're going to have a look at the reactions with hydrogen isotopes. So I'm just going to kill the presentation here, and I'm going to pull up a browser which we can work with for this purpose. So give me a second. If you've got any questions, I might be able to answer them. All right, so we're going to go here. Okay, I'm going to zoom in a bit as well, so it's a little easier for you to follow me along with me. Okay. Okay, 2-to-2 reactions. Okay. So here we go. I'm on nanosoft.co.nz, and I've hit the 2-to-2 reactions over here, and I have put in protium, deuterium, and tritium, tritons, deuterons, and protons. And I've said calcium here. Of course, calcium-40 is the most abundant isotope. But if we, it's not going to produce the neutrons here. It won't do that. So we don't need to worry about that. It's just that I have the table configured so that we can see when that might occur. But anyway, so the first reaction here, you have calcium-43. And this is the most energetic. So if I go and show it like this, you'll be able to see it. So this particular reaction here, 1213027, is producing 12.666716 million electron volts, and it produces helium-4 out and calcium-42. This actually does need a neutrino, but like I said, we calculated in a previous presentation we were likely exceeding 2000 to 2200 degrees because we are seeing the limelight, and that has been calculated to necessitate that kind of temperature. So we didn't need to have a thermometer to know that we were going to that temperature because we are seeing the limelight, and that's already been established. So if we move on, we have tritium here with calcium-46, and then we have tritium with calcium-40. And calcium-40 is the vast majority of the nuclei in calcium that you start with, and you end up with helium-4 and potassium-39. So you start with the most abundant calcium, and you end up with the most abundant potassium and the production of helium-4 and 11.477198. Now, the other thing is you can end up with is if you go down to here, you've got another reaction here with calcium-40, and what's happened is it's produced that this is the next most likely reaction with no neutrino involved. You end up where the tritium has its 2 extra neutrons stripped, and you end up with protium or proton and calcium-42. And this is the main reason why I thought calcium might be suitable, is that it will eat neutrons and still remain stable. And I believe that that is in part why it doesn't matter whether you're fusing or fissioning with coherent nuclear transmutation, you always seem to see a lot of calcium. Now, calcium-40, of course, is double magic, 20 neutrons, 20 protons. It's extremely stable, and it's 10 alpha. It is Dec alpha. And I believe that is so key to why it is so abundant in the Earth's crust. It's so abundant in a lot of living organisms, whether you're spineless or not, or whether you've got an endoskeleton or an exoskeleton, or you're a shell-based creature. It's very, very important to life in general. And here you can see that, you know, the first most abundant reaction with tritium actually leads to production of helium and potassium-39, and the second is stripping those neutrons out. And in fact, if you go down the table, most of the reactions at the top part of the table are using tritium. So it will favour the tritium, energetically speaking, than other elements. And in fact, if you look here, you've got the one that I've just talked about, tritium plus calcium-40 goes to protium plus calcium-42, and that gives you 11.35 million electron volts. And then you jump down 2 and you get another tritium, goes with the calcium-42 you've just synthesized up here, let's say, and it's the first 42 in the table, so this is what would happen. And you get another protium, and you get calcium-44, and you get another 10.5 million 58 million electron volts. So put those two together, you've got 22 nearly million electron volts. Now what happens when you get the 44? Let's find a calcium 44. Well, you've got a calcium 44 down here. So you take a tritium 3 and you do a calcium 44, and in this case you don't get the neutrons, so don't worry about that. It shouldn't happen. It won't happen in the coherent matter. You've got a tritium 3 down here with the calcium 44, and you've got helium and calcium 43. So, and you gain energy that way. So it's whatever forces this thing into a smaller box. And essentially you will end up going up and up the table until you've got a tritium here with no interacting neutrino. It takes the calcium-46, you produce protium, and you end up with calcium-48, which I believe is the most stable, heaviest isotope of calcium that's stable, with yet another 8.8 million electron volts. So you're going to get a whole load of millions of electron volts as this eats the neutrons from the tritium. But that isn't really why I'm focusing on that part of the process. I mean, I did discuss it in the early part of this proposal, but I think it's going to become even more important as we look at what the data is that I'm going to share with you. So I think what I'm going to do now is I'm just going to copy this into the presentation, just for the sake of having a bunch of these things in there. So give me a second, I will do that. And I'll do it down to that calcium-48 one. Or you can run these tables yourself in your own time. So where's the calcium-48? There, okay, so. Okay. And I will put our query in there, which is that one, so that when I share these slides, you'll all know what to do. Isn't that great? Cool. Okay, so, and we'll put the here. Right. So very roughly, we've built our slide there, and we're going to nanosoft.co.nz 222 PHP, and we are doing our HDT and our calcium, and here are our reactions that are coming out of the table. Okay, all right. So what do we start with in our test material? This is from the manufacturer. I've showed you this slide before. And it is mostly 98.76% calcium carbonate, and really we did confirm it was very, very pure calcium carbonate. Okay, so Oh, sorry. Give me a second. Oh no, what have I done? And that shouldn't be there. Got a slide in the wrong place. I'll dump it down the bottom. Okay, all right. Okay, so back in the room. Okay, so this is our calcium carbonate source material, which we can get in mountain-sized lumps. And then this is our gas, if we were using a Mars gas, and this was the assay from the Tokyo Institute of Technology here. And you can see that it contains 0.28% atomic hydrogen. I've argued that the atomic hydrogen can be increased when it's interacting with metals, and I will argue that potentially it's going to be increased in the interaction with calcium carbonate. Anyway, so and then I argued that you know, the OH radical potentially was mazing, and mazing is like lasers, but it's not. It's kind of microwave coherence and self-resonance, and so it actually has an ability to do this kind of self-resonant behavior. And when Slobodan Stankovic was looking at his gas, he observed a lot of OH, and then he found this beam with this spiraling kind of nature, this kind of spiral going through a capillary in a carbon crucible, which he'd cut a hole through using the gas itself. And that looked like one of these coherent matter traveling wave beams that the Russians had seen in the 70s and 80s, or 80s and 90s, I think, and we have observed in the experiments, Vega. So, so this is what is in the gas, and if you actually go to this link up here, you'll see a number of these gases, like hydrogen itself, and I think CO2 or whatever. Several of these gases and water can actually self-maze them also, but it's OH, I think, is the most important one here. And I have this particular slide in here because this shows the flux loops and the figure of eights that are in the Amasa vibrator plate. So you can see that these points where you have these very small spots are, in my view, where the coherence occurs and where you get the transmutation. And this is similar to what we were observing in the ultra review in last week. And you will see that this structure here, this torus structure with these twisted braided segments, is not too dissimilar from, where is it? This, if you can imagine, this is just an electrical kind of idea of how it works, and this is kind of how it actually is in the form of a torus, and this is one that's splattered and the bits have like deposited themselves around the core where the maximum pressure is in this instance. So you can visualize it like this, and we're going to see something later on which is relevant, I believe, where you see this at the end of a structure that I observed on an echo sample. Okay, so calcium production examples. We're going to just talk about some examples. I could have chosen many samples that would have been suitable to get this point across. It really has been observed so many times. It is quite ridiculous, to be honest. But we're going to look at a couple that we have observed, and then we're going to look at a couple other parties have observed, some of which I've talked about and some of which I haven't. And so we have line flux loops. So let's look at those and we'll walk through some of these. So the line triangle, I guess, was the first one that I observed where this was occurring. This was on the outside of the Lion reactor. You can go onto the MFMP's YouTube channel and you can look up Lion, and there will be links to various presentations where you will see this being discussed. But essentially, this is copper and oxygen on the outside here, almost exclusively in spectrum 21. This bit that's been punched out in our famous, now famous triangle shape, which I think is related to these flux loops and monopole structures. And then you have this slug, which has come through. And this slug also has the calcium sorry, the copper, rather, this is copper and oxygen, because this is a piece of copper on the outside that kind of oxidized. So you have copper and oxygen, and basically no calcium and carbon. And then this slug has very little copper, and it has quite a lot of carbon. And we know that this system produces predominantly carbon. And also it has calcium coming in here at 6.4% atoms. And since calcium is dec-alpha and carbon is tri-alpha and oxygen is quad-alpha, this actually represents quite a bit of the weight of this material that is in this slug. So this is one of the first times that I saw fairly conclusively to me that part of this electrohydrodynamic structure that forms is able to potentially produce such pressures as I showed was calculated by Lutz-Leitner, such that it can actually crush matter and reorganize it so that your copper and oxygen ends up being formed into calcium and carbon. And I believe actually, because this is a heavier element, that the loop ends up producing the lighter elements, and the center here, the center is where you get the heavier elements. So in the loop you get the lighter elements, and in the center you get the heavier elements. So there's both fission and fusion going on in these loops themselves, the actual toruses. But I believe that when they cluster together, then they do other weird things like crushing matter and changing things en masse, because you get a self-collapse process. Okay, the second one that we saw on the line series of reactors was this electrohydrodynamic structure, which is on the outside of a magnetohydrodynamic structure. I'll get my worms right in a minute. Magnetohydrodynamic structure that is on the outside of the quartz tube, and it's classical in its organization here. And so you have basically silicon dioxide here. This foam, which was around it, is aluminium oxide, alumina. And then the loop came from one side down and went basically through the corner of this nickel chrome aluminium wire, the heater wire, the solenoid heater wire. And it kind of, that was centered on this center point here, and it may have actually been feeding it electromagnetically. Anyway, when you look at the actual deposit that's on that corner under the SEM, thank you to Magic Sound Labs for the use of his equipment, you get this vortical structure which has this deposit laid down, which has a center focus. And if you look at the material in that center focus, sure, you have the aluminium, the chromium and the iron that's in the Cantal wire. And you also have a little bit of silicon, and you have obviously the oxygen, and the silicon and oxygen are obviously in the quartz. Then you have this carbon, which you expect, and we saw in the triangle. And we also have the calcium, so carbon and calcium. What did we see when we were looking at the slug over here, and I've stepped on? We saw production of carbon and calcium. Carbon and calcium. There's no carbon and calcium here. We see carbon and calcium in the flux loop that went through here. In this, where we have a flux loop going from here to here, this is the North Pole, this is the South Pole. I believe the material is extracted from here and it's thrown down to here. You get these crystals forming, and when you look at the crystals up close, they are these kind of crystals, and they have this synthesized calcium and carbon, and the rest is all in the starting materials. So you've got some consistency there, but it's the calcium story that I'm talking about here. So this is part fusion, part fission going on. Here, in the case of the tungsten versus a Mars gas, you have a 2% thorium-doped tungsten welding rod, and we expose this to a Mars gas. You can see it on the beginning of the end, or the end of the beginning video on the MFMP YouTube channel. And if I've got large samples here and individual samples of various things, it doesn't matter what I'm sampling. There is always some calcium, even down to when the tungsten is lowest or very low down here, you've got very high concentrations of the calcium. And you've also got these other elements coming in here when basically it should just be tungsten and thorium. Okay, so it would appear that it's chewing up the tungsten and it's producing calcium. Okay, and we've got another example here, different area, and you can see where the ball lightning, the Evo, has bored channels through here, and I've sampled some of the spheres in the ends of these channels, these clear spheres that we've seen in other events, let's put it like that, where you have these things boring around and producing these spheres in these areas slightly under the surface. And when you look at that, you again have all calcium in every single samples, but a range of synthesized elements from your tungsten and thorium that you started with, and also a lot of carbon, and so now when you do the reactions actually, and you look, the most energetic reaction, the one that fits into the smallest box, is with tungsten W80. Well, W180 actually is only 0.14% of tungsten, so it's very, very small percentage. So the fact that you don't see, you do see some titanium here, but it's extremely low concentrations. So yes, this might be coming from here, but I don't believe that that is the significant one. The rest of them, the 184, 182, and 180, they even just 182 and 184 constitute 57% of all of tungsten. And what does that produce? Well, it produces calcium isotopes and xenon isotopes. Okay, now we're still looking to do the tests where we use the residual mass process gas analyzer that we have in Santa Cruz at Alan Goldwater's Magic Sound Lab to do this kind of experiment and try and observe the xenon. However, we are seeing the calcium, and what I'd like you to note here, and just stick into your brain right now, is that these calcium isotopes are the heavy ones, 44, 46, 48, right? And remember what I said, that the heaviest isotope of calcium that's stable is 48, and that is what it's preferentially producing from 57% of the mass of the tungsten. And so, it's likely that we've got heavy isotopes of calcium being synthesized. And so hold that in your mind as we move forward. Okay, so Leclerc and Nanospire, he's got calcium here. I've also highlighted zirconium and one other thing here, which we'll probably find is interesting later on. And then is here, you've got more. This is giving you relative, starting with basically water and aluminium. Okay, so that's what they're starting with, and that's essentially what we had in our experiment that we were walking through the analysis of the Ultra experiment last week, where we were synthesizing heavier elements, and I think we got some copper, and we got some zinc, and we got some, what else did we get? We got some molybdenum somewhere, wherever that is down here, and we got some silver, and silver was the heaviest thing that we observed. Okay, so you can see calcium is really quite heavily produced in this system. And also with the work of SV Adamenko, you can see here calcium. And the way to read this is that the little green kind of triangles here are impurities of the original material, where it was supposed to be 99.99% copper, so 4 nines copper. And you see the calcium here was down here in nearly the 10 to minus 4. But after the experiment, the red is after the experiment here, and it's in 10 to the nearly 0.05. So it's gone up the best part of 1, 2, 3, 4 orders of magnitude increase in that. In the case of zirconium, it was down, didn't exist. It did not exist. And the reason I'm going on about zirconium will become important. Anyway, zirconium here is... Zirconium is down here, and it basically doesn't exist, and it ends up producing nearly 10 to the 0. And then we've got silver here, like we observed in the vibration system Ultra that we walked through last week, and it has 10 to the minus 3 kind of level, which is not surprising given the fact that it's copper. This is one of the higher concentrations of impurity. So this is down nearly at 10 to minus 3, and it's going up 1, 2, 3, more than 3 orders of magnitude synthesis going on here. So that is the Adamenko data. And then in the Solin patents, which I'm just showing you the slide here because we've got the annotated translation link, because we're actually going to go and look at some images from this. Remind me if I don't show you them, because they're extremely important to what I'm trying to get across later on in the presentation. But essentially, this is his his 1992 application patent. We're going to be looking at more images from the 2001 patent for direct electricity generation, but they share a lot of similar things. And one thing that they share is that they have, in particular, carbon, nitrogen, oxygen, potassium, calcium here. So calcium is synthesized, and often he was using, interestingly enough, zirconium. So bear that in mind, that he was using zirconium. And then here we have Skiv, and he was using titanium mostly, and he was synthesizing calcium, okay? And in the ball lightning that he saw above, he was observing calcium, okay? This is a discharge-driven transmutation of tungsten by Simon Brink in Australia, in Melbourne. Sorry for him, but anyway. Basically, he is seeing an increase in calcium and zirconium. Calcium and zirconium. So I keep highlighting zirconium. This is going to become important. Right. Is everyone with me? Is everyone with me? Okay, so now what I'm going to show you is what was in the starting material. And this will become relevant when we see the finishing material. Okay, so can everyone hear me? Hi, Elias. Okay, so hi, Bob Kenter. Hi, WP for Truth. Okay, great. All right, so here we have the before material, and this is 100 micron across here, and these are basically crunched up bits that you can imagine were taken off that block that I showed you earlier. And we have two area samples here to get a nice idea of what they contain, spectrum 1 and spectrum 2. And spectrum 1 contains calcium, carbon and oxygen, and it also contains calcium, carbon and oxygen in spectrum 2, which is good. It doesn't really seem to contain anything else. It is calcium carbonate. And if you look at this spectrum here, you will notice that there is this strong peak in the center. Now, why have we got a strong peak in the center? Well, when you are looking at a metal, that's fine under a normal tungsten emission source for electrons in a scanning electron microscope. When that goes to the metal, it can't charge because it's on a carbon or a copper base, and then that's connected to aluminium, and then that's discharged through the grounding in the SEM. And so this allows you to both image the material, and it allows you to get some backscattered electrons and secondary electrons. But the backscattered electrons, they give you an idea of what the elements are, because they go in and they excite the energy levels in the atoms, and they drop down and they release an X-ray or whatever it is, and that's what you see in your EDS. And you get that spectrum back. And so the problem is when you are looking at ceramic, for instance, like silicon dioxide or calcium carbonate or calcium oxide, which we would expect to see in our samples here, is that they don't get rid of their charge, and they end up completely charged, like a balloon you rub on your hair or something. And so you get these blurry images, and you don't get a good idea of what the material is that's in there. So this isn't a problem, by the way, with field emission microscopes, and hopefully we can gain access to one of those, which will simplify the process. And I have another presentation I'll talk to you about in the future. But anyway, with the but what you do to get around this is you coat it with something which is conductive. And what they do is they have a sputter target, and they physically sputter onto your sample a few atoms of, say, palladium or gold or carbon or whatever, that provides a conductive layer, and the actual electron beam can then go through that conductive layer, because that's what actually happens when you do EDS. The beam goes some distance into the material, and those atoms get excited and they emit their X-rays, and that's what you observe. And so by coating it with gold, in this case, is what we did. In fact, I wasn't there. The operator did that and did this whole test without me there. But anyway, this is this gold line here. And so that is what this strong peak is here. And all you do is when you're doing your analysis, you ignore that element. So that element's image and count rate and presence is ignored. And then you just get to see what the other material is. Okay? And so you can see here, I've got the ratios here of the calcium to carbon to oxygen. And you can see that there's taking the normalizing to calcium, there's carbon is 0.7 and then oxygen is 2.4 here. So this should actually be 1,3 because it's CaCO3. It's kind of there. You can see maybe where there's some challenges, and that might have a issue for when we're looking at the next set of data. But we'll go ahead and look at that anyway. But before I do, I kind of want to show you some images from the Solin patent. And this is the one that was produced in, how should we put this, in 2001, which was rejected by the US Patent Office. And it was direct electricity generator. And the reason it's annoying for him is because they just basically said, oh, LENR doesn't exist, and therefore, or cold fusion doesn't exist, or whatever it was. And so, you know, this is not possible, so therefore we can't grant it. And it must be very annoying for him because by publishing it, then he couldn't even protect it in any way. And so that's that. And I'm going to do a full translation of this and a much bigger discussion of it. But anyway, this is the patent here. So I'm going to go kind of full screen on this, maybe like that. So that might work. Okay, so this is the patent from 2002 actually it is. 2002 here, 29th of the 8th, 2002. And it says here, the inventive method for producing electric power variants and Solin-controlled quantum nuclear reactor for carrying out said method relate to nuclear engineering and can be used for producing electric power, electric current, and constructing a new type of electric power stations using a direct transformation of nuclear energy into electric power. Said power stations do not create ecologically dangerous situations because of the absence of radioactive waste and dangerous for population ionization radiation. Said methods for producing electric power using the Solin-controlled quantum nuclear reactor consists in transforming electromagnetic energy into electric energy by means of an inductance coil and controlling the quantum nuclear reactor with the aid of two regulating elements or one electroconductive blank part, or transported liquid metal are used as a conductive material of the inductance coil. Okay, so we know that ball lightning spins. If it has some charge variation or it's able to produce some inductive influence onto an inductor, then it could produce electricity. And so here we have an idea of how we can convert a ball lightning potential into direct electricity in a non-contact way. We do know these things like to attract each other, and we have postulated that that might be because of a magnetic interaction with each other, even that it may even send out a magnetic beam, and the magnetic beam actually does look like it's spinning. So if you remember in the Vega experiments in extreme interactions video, you had a beam, coherent matter traveling wave here, and you had another one, and before this one even crossed the path of this one, it saw the beam coming out of the front, and that moved it around. So you could orient around the sample some inductor coil that picked up on this magnetic beam that comes out of the top of the structure. And it's actually very, very interesting, because if you look at Solin's patent, I will just pick up one of the examples here. You know that he knew what was going on. Because here you've got your coherent matter condensate in here, and it spins round. And this 42 here is the inductor coil that is picking up the energy and converting it directly to electricity. Yes, my friends. Yes, my friends. Solin told us how to do this in 2002. And you know what? He didn't get the patent. It's published. You can use it. We are very close to getting direct electricity. Maybe we don't have to do it in such a complicated system as this because we've got better understanding. Have we? I don't know. Let's try and have better understanding. But I think that Solin is absolutely on the money with his system here. And he's got a couple of slides that you can see of these kind of arrangements here. And he actually feeds liquid metal in to cool the inductor coil here. Okay, and this is, I believe, might be wrong, but like I say, I'm going to translate the patent fully. I believe that this is actually the vortex that is produced in this quantum coherent material here. And here are actually photographs of the process ongoing in various stages. And looking at it from, this is the slug that's left over. Anyway, so I'm now going to pick out a couple of images, and I've kind of like zoomed into these in the translation that I'm doing. But here are the things that I want you to look at. These are what he says are on the inside, these kind of structures, and we looked at these before, where you have these kind of like ring-like structures coming from a point. And he's saying that these largely go across the surface, and this is actually on the inside of these spherical structures that are the places where the nuclear reactions occur. Unfortunately, it would have been, you know, unfortunately, they're not as good a quality as you would want. This one, he actually refers to this as a vortical structure, and you've got the curves coming around this side, and you've got the curves coming around this side, and it certainly does look like a vortical structure to me, so I think he's probably on the money there. And so he's looking at this structure here. This is the vortical structure, and here's some features on that. Here's the one that we looked at before, which looks exactly like the ones that we've seen in line, both on the quartz and in the actual X-rays and so forth. So if we can get that and zoom into that, that's that one. And then I'm going to show you some other ones here, which I think really nail this. So here again, you've got these radial points on here. And here is a zoomed in section. And you can see you've not only got the curved sections here, you've also got these waves on the curve. And in his patent, he describes what this means in terms of quantum mechanics, what is actually going on in the coherent matter structures, and why you have the curves here and why you have the curves on the curves. So I've got it here. This is Fig 30 from this. And I believe that this here is a zoomed in version of looking at that particular structure. So you're looking at a smaller section of here. Again, these are actually monochromatic, so but I think we're going to get much better images. I think we're going to get much better images because I think we're probably doing exactly the same thing. And here is something that's on the surface in a different place, these kind of like squiggly bits. It doesn't seem so clear. You almost have to blur your eyes and step back and kind of imagine what it is. But these are more clear, so I think, you know, he's done a good job with getting these resolved even in this monochrome form. Okay, so these are the ones that I think are the most important structures to consider for our purposes. Okay, so that is some detail about the Solin patent, and then it will make sense as to what I'm just about to show you now in relation to that. Because, my friends, this is what we see when we gold coat our calcium carbonate that's exposed to Slobodan Stankovic's HHO, or oxyhydrogen generator. Okay, I have 3 samples here that the lady took, and in sample 14, this is a fleck that's fallen on this part of interest and maybe is somehow bound to it by the gold deposition. And you can see that this is essentially calcium, oxygen and carbon with 0 nitrogen. 0 nitrogen. This is going to be important. Why am I saying 0 nitrogen? Anyway, on 13 here, you can see our gold peak, gold coating peak here, which follows through to this one, which follows through to this one. So we're ignoring this gold coating peak. But what we are seeing here is oxygen and calcium, no surprise, and a much higher level than 0 of nitrogen. That is going to be important. Why are we seeing this nitrogen appearing? And then we have silver. We have silver. Why are we seeing silver? And then carbon. The carbon has come down somewhat. But the silver here and the nitrogen and the carbon are not registering as white. And I've told you before that that means that the software is not certain in them existing. And the reason is at this point the counts are low. So what's happened is the operator has set the sample time to a certain amount of time. It's beamed out the electron beams to the sample and they've come back. And it's counted what they found. The problem is that you can see over here in sample 14 that it has 1,000 plus counts up here. Here, you've only got 60. Now, why is that? I mean, you've still got like a broad spectrum here, but you've got more noise. Look at the noise floor. The noise floor here is very low, but the noise floor is higher here. What's going on? Well, the reason that is because this spot is in a crack. So the electrons aren't really getting there to excite the material anyway, and they're probably going to get taken away mostly by the gold coating anyway. So this is what's going on here, is that you're not getting a lot of electrons exciting the material, returning their characteristic X-rays. And so yes, it is seeing silver, but during the allotted sampling time, it didn't see enough samples to be certain that this is what's happening. But fortunately, the operator also chose a peak on this ridge here. And this is sample 12. And in sample 12, it reports largely in the same order of silver being synthesized. Here, silver, okay? And it's certain about the silver. It's not, again, so certain about the nitrogen, and not so certain, even the carbon's like, the carbon's a major constituent. Down here, it's not sure about it, okay? But the silver is coming into certainty, and this really is the right peaks. And over here on the left, I've done my homework to check it wasn't some peak overlap. And the primary X-ray here of silver is at this 2.98, and there's a secondary one at 3.151. And you can see both of these on each of these two samples. And what's more is you can see that it does not exist at all on this fleck, which is fallen onto here, which is not part of this radial wavy structure that has a wave component running this way and a wave component that's running. You've got an annular and a ring wave component in there. And so this is, for me, absolutely certainly silver, and it does not exist even on the same sample with a fleck that appears to not be part of this structure, which is reporting the gold line. So it isn't like an impurity in the gold. Now, maybe there's some coherent matter on here and it did something with the gold and produced the silver. I don't think that's very likely. And I'll tell you why I don't think it's very likely. Because silver has actually been observed quite a lot. And so Miley did this study, which I talked about in the last presentation in 2009, and he found that 5 labs out of 16 in 2009 saw the production of silver. Now, why would that be? Well, I'll tell you probably why it is because they are using deuterium and they are using palladium. And if you take deuterium and you put it into palladium, some of the reactions, as you will see, produce silver. And so for me, it's not that surprising that they were seeing silver being produced. Interestingly enough, as I pointed out, calcium is quite common. Seven of the labs reported calcium. And in the previous presentation we were talking about, or one before the previous presentation, we're talking about how many labs produced iron, and that was the most, 11 out of 16 labs in 2009. But here we have 5 labs out of 16. It's bordering on a third of the labs had synthesized silver. And that wasn't even including Ken Shoulders. And in Ken Shoulders at ICCF 10, he showed both the production of calcium in a nickel in aluminium oxide reactor and silver over here. And it's almost the heaviest element that he has synthesized, silver over here. Okay, so he produced calcium and he produced silver in a nickel, and presumably it was an EVO, and the EVO's coming in and it's hitting the nickel and it's producing calcium and silver. Where did we see silver? We saw silver in, and I presented this in 2017 in my manipulating matter presentation in Copenhagen. So you can go and see me discussing this with in relation to the Echo reactor. But this was observed in Suhas-Ralkar's nickel foil preparation. So we have nickel here and we have nickel foil preparation here. Now I know that Dave is looking to do a vibrator test with nickel foil. He's looking to source some nickel foil, and I predict that he may see more silver than we saw in our aluminium system. And the other thing that I wanted to show you here is this kind of torus-like structure on the top here that has these bands going around it, which looks, in my view, and I discussed this before, it looks very similar to this. The distance between these and the segments like a candy stick. Yeah, I've got my mugshot over the top. I'm talking about this here, this system here. And if you go down to where I was looking at there, so we got that here, this ring here with these segments. So I believe that this was a coherent matter traveling wave. It's like a bunch of EVOs that kind of twisted up into a blob and kind of flew off. And it's a bit like the diamond one that we saw in the Vega experiment from Henk, which I shared in Azizi. But in this case, this one is, wait for it, 94.5% by weight silver. 94.5% weight silver. And it has 4.1% by weight of nickel. Now, what was he using? Well, I've already given you the hint that he might have been using nickel. This is the reactor, and so I have a bunch of animations here. And so there is a metal plate in here, and there is an electrolyte, which is nickel sulfate. 16.5% by whatever, plating solution. And that is raining down, and you can see the specifics in this next slide here. And this is interesting because what Suhas-Ralkar was doing in his resonant ion implantation technology was he was not only using electrical discharge in the same kind of manner as the plasma flow discharge of Bogdanovich, which we know produces these long-lived luminous plasmoids 2 days after the exposure. But it also produced the ball lightning structure, and it also produced transmutation, and it also produced a range of black and luminous plasmoids during the experimentation. So he's doing that, but he's also got sound. And so he's actually vibrating the metal sample with sound. And he has discharge at 200 volts, and it's at 300 kilohertz DC. So he's doing 300,000 pulses per second of DC discharge. Okay? And there's more detail on there. Okay? And plating solution, 16.5% lab grade nickel sulfate by weight in deionized water. So he is using nickel sulfate, and guess what he is ending up with? He is ending up with this, which is a pure lump of silver, but that isn't all that he ended up with. And this will become, I believe, relevant. He also, or rather we observed in one of these strike marks, so where you have the discharge between the, there's a discharge between these two, anode and cathode, whatever it is. He is basically, how should we put it, on the nickel foil, you are getting these agglomerations, okay? And this is on the nickel foil, and you can see that a good proportion of it is nickel. We've got nickel here, 12.7%. And you got sulfur because, well, it's nickel sulfate. But you've also got calcium and iron and chlorine. But what, what I'm looking at here, actually, is the spectrum over here on the right. And this bit stuck out as being brighter, so I thought I'd check it out, because brighter in this mode, this backscatter electrons, that can give you an idea of what the element is. So I looked at that, and spectrum 29 is 31.9% by weight gold. Okay? But the interesting one here is, and this was part of my argument we're coming on to, is we've got calcium, but we also have palladium. Palladium. Okay? So what I was saying earlier is if you take palladium and you start putting deuterons in it, you end up getting silver. And in fact, when you go through his material and different technologies, you end up with all of these elements produced, including zirconium here, and calcium, and palladium, and silver. Okay? Right. Did we observe silver last week? We kind of did in our aluminium foil. So in spectrum 44 here, in this, and it's fused into the kind of like eaten away part of the vortex in the center. This spectrum 44 here, you've got calcium and copper, but on this slight outside area here, you've got silver being synthesized. Now this is a very low rate, but we only ran this experiment in the tens of seconds. So I reckon if you ran it more aggressively for a longer period of time, you got more coherence, you would end up with more potential silver being synthesized. Now, why would silver be... What we find is that the silver tends to be on the outside, and there's another sample that we showed last week where the silver, if you remember, there was a splat, and on the outside of the splat there was silver. And we found that in the ultrasonic system of Amasa, you had diamond in the center, then you had double diamond, magnesium, in the vortical bands coming out from that, yeah? And then around those vortical sort of bands, you had chromium, which is double magnesium. And so the further away you got from the core, you ended up with actually heavier elements. Okay, and so perhaps that is what's going on here. That you know, you've got the copper is in the core here, but you've actually got silver on the outside, because that was actually true also of this splat. But I'm not going to pull that up now, but it was. You can go back and look at the video. Okay. All right, so making silver. So potentially it's getting thrown out. The silver is getting thrown out. Why? Because it's fermionic. Both isotopes of silver, the nuclei are fermionic. And I believe, as I've argued before, that inside the EVO, the actual nuclei can be completely stripped of their electrons. So they're just the nuclei. And if you're trying to squeeze all the nuclei into a small box and you synthesize by rearranging some silver, it gets chucked out. It gets like sprayed out because it's all fermionic. It can't live in this particular structure. Okay, so now where am I going with this? How can we get to silver? How can we get to silver? Now, I'm just going to run through my next slide here, but I'm then going to take you to a presentation I did a long time ago. So this is path to silver. So one potential path to silver is carbon plus oxygen ends up with calcium. And what I'm looking at is just the protons here, okay? It'll become important later, the neutrons, but at this stage I'm just going to talk about the protons here. So proton defines the element, not the isotope. Okay, so effectively, if you combine carbon and oxygen, you end up with silicon. So it's almost like carbon and silicon ends up at calcium, but two carbons and oxygen ends up at calcium. If you take calcium and calcium, you end up with zirconium. If you take carbon and zirconium, you end up with palladium. And if you take isotopes of hydrogen, I've just put protium in here, and palladium, you end up with silver. Okay, so this path is kind of roughly what we're saying here. And, you know, I've got observed in many systems, observed in Lion, Echo, and Brink. And I've done presentations in the past on the synthesis of zirconium. And one of those referred to some work by a chap called Bolotov. And we're going to look at his patent now, because that is going to help us understand where I'm coming from. If I can find the particular window here. Okay. And so it's about 3.5 years ago I shared this presentation called What Really is New Fire Fuel? And you can look at that in your own time. And I talked about the elemental abundance and the synthesis from ball lightning and how that occurs. There's that chart that I showed you earlier. And here's the Echo ultrasonic fuel generator. And we're talking about the fact that he made lead and niobium and tin. And why tin? Because tin is like fissioned lead, or it's something that you can use to make lead if you add it together. And I walked through that. And this is the kind of like various methods that I observed different strange radiation tracks, both on Logitech 910C, in plastic that was exposed at a distance, in plastic that was in contact, on the fuel itself, and on X-rays. So all from this one sample, which was ultrasonically produced in this thing, we observed all of these different ways of observing strange radiation track. So this was my baptism of strange radiation track, the baptism of the new fire into strange radiation, which led me to believe that it was so important. And these are tracks which I've showed you earlier. And these are tracks from actually SV Adamenko of strange radiation tracks. And we now know, in fact, as far as I'm concerned, that this is the interaction of a coherent matter traveling wave on the material that is being interacted with. But anyway, talking about the disappearing tungsten, and Suhas Ralkar said, you know, I put this tungsten in to my fuel processor because it's very hard, and the idea was that it would smash up the less hard nickel and so forth to make smaller particles. And he was basically using that as like balls you have in a ball mill to smash up things that are less strong than the balls. And what he couldn't understand is the tungsten had all disappeared. This was another instance of tungsten disappearing, but in this case it was through ultrasonics. Okay, and so I work through this process here of he says, you surely remember my telling you our tungsten powder based ultrasonic milling during the fuel preparation and then allowing part of the tungsten powder to remain in the fuel. There was no tungsten in the fuel. And so basically, where did the tungsten go? And so I came up with a hypothesis that it could have produced the lead and so forth from the tungsten. But there's this whole thing about zirconium down here. And I won't go into it into too much detail. But if we go down to here, Bolotov had worked out that zirconium was synthesized in the earth because zirconium is effectively double calcium. And this is in his patent. The inventors also noted that zirconium was related to calcium within the earth's crust. Zirconium oxide is synthesized from calcium oxide as follows. Calcium oxide plus calcium oxide goes to zirconium oxide. Consequently, zirconium dioxide was referred to as double calcium oxide. So here you are with me trying to detail why we are going through this process here. And so this was his patent, which I think it was awarded. I can't know, maybe. But this was priority November the 5th, 2001. So very shortly, this will be available for anyone to use. And he's putting a pulse discharge into this reactor, and he has a molten material in here. And it's quite detailed, but this is the patent that I took that phrase from, where he is observing this reaction somewhere here, this one here. So that's the section that I took out. Okay, right. Okay, so the path to silver is effectively, you could argue that it is two calciums and 2 calciums to get to your zirconium, and 2 calciums is actually 4 carbons and 2 oxygens. 4 carbons, 2 oxygens. Okay, and then you add another carbon onto your zirconium that you synthesized, and you get palladium. Okay, and then all you need to do is take your protium or your atomic hydrogen that is in your HHO, and you add that to palladium, and you get silver. Okay, and what we know already is that because of the work of, and I've just killed my preview window, so sorry about that. Don't go away. Give me a second. Okay, so I'm going to go and show you that thing that I showed you earlier, which is in the Solin workshop. We know from what I'm showing you here that what we are creating, I believe, in our observations on the HHO on the calcium carbonate, is these structures. Now I'm going to actually go and pick up the full resolution of this SEM image so that you can get a full appreciation of how this compares. So give me a second and I will do that after. Okay. So we will get up Solin's. Okay. So on the left, I'm going to have Solin's image. And on the right, we're going to be moving around our image from the SEM of Slobodan Stankovic's exposed calcium carbonate from Vietnam. So here we go. Okay, so you have these ring structures and you have this waviness. What do we see on here? We see ring structures and waviness. Let's have a look over here. Ring structures and waviness. Yeah. Ring structures and waviness wherever we look on this sample. Now this area, I mean, if we look into the zoomed in area here, maybe find a suitable area, maybe just this bit here, you can kind of get a similar feel for what it might be here. And then there is this area up here, which is kind of like, it's lost its ringiness here, and we've got these kind of globule bits just around this area, and this is remarkably similar to what he's sharing here if you really blur your eyes and trying to squidge one into the other. Maybe. I'm not so convinced about that, but anyway. Yeah. It would just be nice if these were more than bitmaps, but I think pretty much we're dealing with the same thing with this and with this and this kind of thing. Okay, and so what does this mean? What is the significance of this? Well, it means that in my view that this is a quantum coherent nuclear reactor that's being created. It's being created by the coherent matter. He says it's coherent matter. We know that the ball lightning structure, the coherent matter that interacted with the 10 yen coin, produced microball lightning that transmuted the oxygen on the copper oxide to sulfur, and we saw the little snowballs on cobblestones moving around and doing that. So we know that this is producing ball lightning, and we've seen the monopole structure on there that was the macro structure of which that played as one part. And so we know that HHO can produce coherent matter. We know that it can produce ball lightning. We also know from the work of Yul Brown that it can transmute matter, and what you are seeing here in this is the actual structure that is equivalent, in my view, to the coherent nuclear transmutation zones as defined by Solin in his quantum coherent nuclear reactor. And the other thing that I'll say that you're seeing here is that Solin says that this is surface structure, and he is actually, it doesn't have a massive depth. You can see that it goes down and it's quite smooth in this lower area here. But it does have this tail here, which looks distinctly different. And I wonder if this isn't the monopole in here and this is some sort of structure coming out. And I would like to do a lot more experiments and see if we see this kind of almost different tail here. Are we seeing something? Is this a trail of something that came in and it blew up at this point? Possibly. I don't know. This for me is the most interesting bit of this overall structure in my view. This kind of like different tail that we see here. It might have just been that when this structure blew up and sent out this coherent sort of traveling wave, whatever it is, this was already broken and it just interacted with the material in a different way here. I don't know, but I think for me, what you have here, in my view, is 100% proof. If this is the same as what Solin saw, then you are seeing the effect of a quantum coherent nuclear reaction process, and that we have a potential that we are producing silver on here. We've observed silver produced in many different like systems, and we're getting to the point of maybe this is exactly what's going on. So I'm going to build another slide now. If you'd like to ask some questions before I go to it, I'm just going to actually walk through the reactions on the nanosoft.co.nz. But I've already done them, so just to save time. But I actually need to copy. I need to copy them into a series of slides. So because there's something that we need to answer that it's showing us that I think we've already answered it, but it's only going to become clear in the context of everything that I've said today, if you've been keeping up this far. Okay, it looks like a stack of souls. Okay, cool. So yeah, if people want to do the ultrasonics, I think Dave's already ahead of the game. But I've shown you both an experiment by Suhas Ralkar, where he's using nickel sulfate, which is something that you could put in water to promote the production of silver, or the work of what's his name, Ken Shoulders, where he was using nickel. And so in those two instances, you're synthesizing silver. Why are you getting the production of silver? Potentially, in fact, I'm just going to pull up a slide here. It could be as simple as this. Let me show you. This is our wonderful periodic table. And so you start with nickel, and it's dropping down the periodic table, and then you're adding a hydrogen or deuteron. Dropping down, or it's like a two routes to the same thing. It's going across the table by adding a proton and producing copper, and then it's dropping down the table, and it's dropping down the table to synthesize gold. So what I'm basically giving you is potentially a clue on how you you get to synthesize what everyone wants to synthesize. But anyway. Okay, all right, I'll move back to what I was doing. So it might be that nickel sulfate is easier in my view. To use aluminium as your base because it's cheap, and nickel sulfate I've got some in the other room, and maybe I'll do that experiment, but I'll give you a week to try and beat me to it. And then you basically run that with the nickel sulfate, and maybe you end up with the gold that'll be focused into the beam, or the coherent matter structure, or yeah, I don't know. But anyway, I'm going to get on what I was doing, talking to myself now. All right, okay. Let me just drop these in. Just take me a few minutes. Like I say, I've already done the work. I just need to copy it into a slide. So. And I'm going to go backwards with this. It'll make sense. Honest. Okay. Okay. I think we're done. So, obviously. So this is our path to silver. The path to silver. So I said there's going to be problems in here when we're not just talking about the protons in the elements that we are referring to, because as you go beyond calcium, you need extra neutrons to stabilize the nuclei. So I've already argued right in the beginning here that if we have this system and we are creating a 2 times 10 to the 21 pascals, 5 orders of magnitude, 100,000 times more sort of pressure than is in the center of Sol, our sun, and that it is in the range of the density, nuclear density of a pulsar, which is a neutron star, then conceivably we could readily have electron capture and the synthesis of neutrons. And so then, you know, the observation of something that I'm going to show you is not too difficult to understand. But let's start with the equation that is observed in Lena field, which I believe is the cause of these many of these Miley results, where you have this 5 labs reporting the production of silver. I believe that that is because there's these isotopes of palladium, which they are always looking to try and use, because palladium was determined in 1876 or whatever it was by Thomas Graham IFRS, that it was stored the most hydrogen isotopes. There was only protium known at the time than any other metal, and so that was a good candidate, and also it's a heavy element. So anyway, the point is, quite a lot of people have observed the production of silver, and the one that I suggested when I was in Boulder, I think it was Colorado, and there was Mike McCubry up there, and he said, blah, 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 105, and I said to him, well, that will be because it's deuterium 105 is going to silver 107. But anyway, the point is, silver can be synthesized from either protium or deuterium into these isotopes of palladium, and you get silver. So we need to kind of get to palladium first. Well, how would we get to palladium? Well, if we look at adding carbon into zirconium, you can use these isotopes, zirconium 96 for 12, 94 or 92. These are carbon 12 and carbon 12 to 96. So if we actually have these isotopes of zirconium, then we can get to palladium. Now, what palladiums are we meant to be getting to? 105, 108, 106, okay? Well, you can get to 105, 108, 106 here. And in that case, it's with 12, 12, and 13. 13 needs an extra neutron. This one needs an extra neutron to get to 104, and 104 down here can do carbon 12 to zirconium 92. How many isotopes are there of zirconium? 1, 2, 3, 4, 5, 6. We've got 1, 2, 3, 4 covered here. We haven't got 90, and we haven't got 93. Okay, and they constitute about percentage in the crust. There's no 93, so forget that. Don't need to worry about 93. And 90 is unfortunately 51% of the crust. So if we essentially we've got the other isotopes, but we haven't got the one that is the majority of zirconium. So that's unfortunate. However, all we need to do is start adding neutrons there. So where are we going to get the neutrons from? Is it because we are compressing this sufficient to get the neutrons? Or is it that we are getting them from another pathway? Well, let's put that aside. So we can start with isotopes of zirconium that exist and that represent around about 49%, and we can get to some silver. It might be that, you know, specific isotopes are more prone than others to transmute, and that might determine the transmutation path. But we can use standard carbon. So actually, so far, we can use standard protium, and we can get both isotopes of silver from a couple of isotopes of palladium, 106 and 108. And 106 can be synthesized here, and 108 can be synthesized here, both with carbon 12. Carbon 12, carbon 12, and an isotope of zirconium gives you the isotopes that you need to add your atomic hydrogen, and you end up with the silver that you require in your end product. Okay, so we're good so far. The problem really comes when you want to go from the claim of Bolotov that he observed, where you have calcium and calcium going to zirconium. Well, firstly, if you take the calcium isotopes here, then they essentially... Oh, I've got a fly with me. It's joined me for the evening. You actually need heavier isotopes of calcium. In fact, there's no calcium-40 in here. And even then, with these heavier isotopes of calcium, the highest isotope you can synthesize is 92. And as I showed you here, you're looking for 91, 92. Yeah, so 92 is there. So you can get a fair number. So it might be that the combination of 4.6 and 3.0 and 0.9, this is the most you could get in terms of silver, unless the whole thing becomes coherent as a silver blob and then gets transported elsewhere. So, you know, this would be 4.7, 5, 6, 7, 8.7, you know. A combination of this might be the limit at which the production of silver could occur given these elements in here. But this needs more neutrons. All of these need more neutrons because the vast majority of calcium is calcium 40. But as I showed you earlier, where is it? I showed you earlier by running the calculations with tritium. If you have tritium, it actually goes quickly up through the table to produce the heavier elements, isotopes of calcium. And actually, I showed you that when you fission tungsten, and bearing in mind I've just said tungsten disappeared in the Amasa vibrator, not the Amasa, in the Echo, Suhaus Ralkar's fuel generator. Tungsten completely disappeared, but it also transmuted here. And remember I said it transmutes to the heavy elements of calcium, 44, 46, and 48. 44, 46, 48. What are we needing down here? We are needing 46, 44, and 48 predominantly would cover most of the transmutations to the isotopes of zirconium. Okay, so there is a potential for a forward-back process here, and then that gets into, you know, what is going on with this. Now, this is a slide I haven't prepared. This isn't a slide I haven't prepared, but I have it in Excel. I kind of half did the work, but I want to get this out the door, so you're going to get it in this form, so sorry. I'm going to talk about a presentation or a STEAMIT blog that I made a very long time ago, and it'll suddenly seem relevant here. And it is here. And this was over 4 years ago, so maybe 4.5 years ago. Could the smallest of charge clusters help explain the new fire? Right, well, anyway, skip all this. What I'm referring to is this image here, which is called the CNO cycle. So you may have seen something similar when I was talking about what really is the new fire. It's effectively... Where are we? It's what happens here, the CNO cycle. You can go around this cycle by keeping adding in protons, and 12 acts as a catalyst. Specifically, it makes nitrogen 13, carbon 13, nitrogen 14, oxygen 15, and nitrogen 15. Now, not all of these elements are stable. What are not stable? Well, if you go from carbon 12 to nitrogen 13 by injecting a proton, you get a gamma. Now, we don't need to really worry about the gamma because we've got coherent matter. So it's basically like a force shield. That energy is going to be absorbed by the coherent matter and it's going to be dissipated, and that's just going to provide some nice glowing stuff going on. And keep the system going. So we synthesize 13 nitrogen, but that is unstable. So that will decay, producing a neutrino. Now, what can a neutrino do? A neutrino can interact with a neutron in the core, destroying the antineutrino and releasing an electron. So the electron would then feed the process, and you would produce a... what do you do if you get a neutron? You get proton, right? So you get proton electron, and you get rid of the antineutrino that binds them or is part of their collective. It also produces a neutron. So here we have a neutron. We got a neutron coming out of here. No, sorry, a positron. Forget what I said here. We got a positron coming out here. And so the positron can interact with an electron, and that produces a 511 keV, 2 times 511 keV X-rays, gamma rays rather, and they go off in opposite directions. But of course, they hit the coherent matter and they energize it. So don't worry about the positron. So the 13 nitrogen decays, it releases a positron and a neutrino. They can interact with the matter in there, and then we get the carbon-13, and carbon-13 is stable. A proton goes in here, and then we get the nitrogen-14. This is stable. Go through, we get another proton gamma coming out, and we go to oxygen-15, unstable, positron out, a neutrino out, and then we go to nitrogen-15. Nitrogen-15 is stable. So as I said here, 4.5 years ago, could the Shoulders interpretation of the mechanism enable, for instance, the CNO cycle on the desktop, which is part of stellar synthesis? Is this why Suhas-Ralkars claimed he saw an excess increase when he added carbon? Excess increase when he added carbon. This would also lead to the production of nitrogen in situ. I wrote this 4.5 years ago. I cannot change it. It's fixed into the blockchain. Why would it produce? So you start with carbon in your mix and you go through the CNO cycle because you've got atomic hydrogen involved, okay, in a compressed system, okay, compressing it into a small box. And you go around this loop, okay, and you're producing high energy helium. This produces a high energy helium, neutrinos, and positrons. And the positrons can come out and annihilate an electron inside matter, and then essentially producing 2 gamma rays. But if the electron is part of a neutron, then it ends up making a proton and so forth. So basically, you've got a whole smorgasbord of things going on here, but you end up by producing some nitrogen, which is stable, the nitrogen 14 and the nitrogen 15. What do we see in our data? We see this. When I show you, what did we see? We saw not there, not there. Where did I put it? Did I delete it? Oh dear. Oh, there it is. There we go. We saw this. We saw that we didn't have any nitrogen to begin with, and we ended up with some nitrogen, 14% nitrogen or 12.5% nitrogen here. Now, so we have a scenario where 4.5 years ago I suggested nitrogen should be synthesized, and we have a scenario here where we look like we need the CNO cycle to produce different elements that will get us to you know, where we need to be, and it's kind of providing it here. So I actually have this chart here, and what I've shown here, I've got the CNO cycle here, and I have this element atom percent here for the sample zones, which I showed you on the previous slide, okay, although this isn't a slide. And what you're seeing is that this is the bit that is, well, let's show you. 14 is the bit that is essentially not the material that was exposed to the coherent matter nuclear reaction. So this is 14. And then 13 and 12 are part of this overall structure where the nuclear reaction occurred, or the influence over which it had. And here you are seeing that the carbon here is 0.4. It's by far the highest. So this is the partially affected material, and the carbon could go away, or it could combine with the oxygen that is coming from the oxyhydrogen gas, leaving more atomic hydrogen, and go away as CO2. So the carbon could grab oxygen and take that away as CO2, leaving you with some calcium oxide. And so But the other thing is you observe the oxygen drop as well. Now, some of the oxygen can be taken away by the carbon in the normal decomposition process of CaCO3. But what you see is between those two sample points, the nitrogen's 0 on the mostly unaffected piece. But the nitrogen is higher, and then it goes up higher. And this is, even though this is higher nitrogen here, the carbon's higher here. So could this be a CNO cycle process going on here? Now, there's no oxygen 16 in here. There's no oxygen 17. In fact, there's no oxygen 18 in here. You can only synthesize the oxygen here as one that decays. Okay, so this process is not adding oxygen to the process. And so oxygen is being consumed somehow. And I already walked through the process that if you want to create calcium, that is carbon plus oxygen. So that can consume carbon. And carbon is synthesized by eating whatever material you give it. Anyway, I'm not being very clear here, I have to say. It was clear in my head when I thought it through earlier. But what you're seeing here is something that, to me, suggests the CNO cycle is going on. And so this requires protons. I'm arguing that protons are coming from the oxyhydrogen gas, okay? And that if you have a positron going into matter, or in this reaction, in this incredibly intensely compressed state, that the positron can go in and destroy the electron in other nuclei and produce an antineutrino and a neutron. And so neutrons could be synthesized in this overall coherent matter process by the CNO cycle, but the output of these positrons interacting and synthesizing neutrons. So we get the heavier neutrons to lead us to the heavier isotopes of calcium, which lead us to the heavier isotopes of zirconium, which then allow us to get to silver with the introduction of another proton. And so I believe that what you're observing in this particular slide here is not only something that looks like a coherent nuclear transmutation reactor and process, it matches what was observed and stated as such in detailed fashion in 1992 following a long energetics research program, I imagine, by the Soviet Union. It's a dead ringer for the process. And in it, you have the elements required and the proportions of outcomes here and that I've just been discussing here that point to a stellar type synthesis going on a micro level, leading to the consumption of oxygen, which produces more calcium. So the oxygen goes down, the calcium goes up, and nitrogen goes up. Where's the nitrogen coming from? I think it's from the CNO cycle. There is neutrons involved because you get neutrons synthesized, and they lead to intensification of the amount of calcium of a higher isotopic level, which is required, as we saw here, for our synthesizing the elements of zirconium, and also for synthesizing the isotopes of where is it? We need to have more neutrons going in to synthesize the heavier elements of zirconium, so that we get a better scenario for producing palladium, which then leads through to our silver. I hope that was clear. Maybe it wasn't. So does anyone have any questions? Because maybe I can answer. So what I'm saying is we have something that looks like it is a coherent nuclear transmutation system. It looks like one that is described in the Solin patents from 1992 and 2002. The inputs are calcium carbonate and HHO. HHO was shown by Yul Brown and ourselves using a Marsa gas to transmute elements. So we're good understanding that can occur. It looks like it did it in our other experiments that I've shared with Slobodan Stankovic. Slobodan Stankovic observes transmutation, and we've got a transmutation that has both a historical record of occurring, a record with our own experiments in water-related systems, and in other experimenters' work, and it's producing silver. And we could be in a scenario where you are getting rid of the tritium laced water. You are generating energy and you are synthesizing an element that is far, far more valuable than chalk. It's a win-win-win. It's a win-win-win. Why would you not want to do that? Just out of curiosity. I mean, they're looking to spend 30 million to dump it into the sea. Maybe there's someone out there that's curious enough to see if they couldn't use this to create an industrial process that converted chalk into silver. That's great. That's great. And tritium wants to give up its neutrons. We showed that it preferentially wants to do the transmutation here in this slide here. It preferentially wants to take those calcium isotopes and lose the extra neutrons and synthesize heavier isotopes of calcium, which is exactly what you need. I believe that, firstly, we have to be aware that most of the water at Fukushima is going to not be tritium water. It's going to be mostly normal light water with maybe some heavy water, not the super heavy water. It's going to be mostly light water. But for the component that contains deuterium, and the component, because you can see here, deuterium preferentially is above protium. In fact, you can't see any protium on this entire table, and I've included it. You have to go quite some time down. So deuterium likes to also work preferentially. And so they're not worried about the deuterium, but you can imagine with a lot of neutrons flying out of that melted down reactor, when you put water there, you not only get tritium formed, you also get a lot of deuterium formed, but that's not a radioactive hazard. But I think this water would very, very rapidly produce silver. I'm just saying that that's what I think would happen. When you electrolyze this and you produce a Marsa gas or quality HHO, and you put this on calcium carbonate, you might just get a lot of zirconium, not a lot of zirconium, a lot of silver. What we observe, we get a lot of silver. And what's bad about that? You can literally have a process where the calcium, these kind of blocks are running through with the jets on them, and then you have a machine that just scrapes off the bit off the top, and then it runs round in a cycle. It just continues to run round in a cycle. And you end up with this byproduct that is rich in silver. And according to this, this might just be a surface process, or it might be a partial bulk process. But you are looking here at, where is it? If you look here, we're potentially going to be yielding nearly 8% silver off this surface area. And so you skim that off and you're converting maybe 8% of the calcium carbonate to silver, and then you run it through again and run it through again. Whether you're paying for the process by the energy or you're paying your process by the production of the silver. Now, you could choose a different element. I just think that calcium, because it loves neutrons, in my view, it looks like it loves neutrons. The data shows that it might like neutrons. The Parkhomov reaction table shows that it should love neutrons. And neutrons want to find a better arrangement in a coherent matter system, is my understanding. I think that calcium carbonate, because it can rise to well over 2,000 degrees, it can produce those extra cold neutrinos that can help facilitate the process. I think that probably we may have enough evidence already to say that this will work. It was a good guess based on a lot of historical data. We have the supporting evidence that we got here. And you know what? The experiment that we did, Slobodan and I, did not take that long. We can replicate that over and over and over and over and over again very quickly. In fact, Roy Shinamaza, if you're watching this presentation, you can use some Marsa gas on some calcium carbonate and look to see if you see these structures on there. Now, I have one proviso, maybe the exotic vacuum objects that are sitting on the top of here. I've done some sort of fission process and produce silver. I don't know. But my view is that the silver could quite likely be real. I would like to look at more of the material that we produced in that first run. I would like, I left some deuterium with Slobodan Stankovic, and I would like him to enrich his electrolyzer. I know it's only a small amount, but I'm interested to find out whether we get a different element produced or whether we get a higher concentration of silver produced in these quantum coherent nuclear reactor trademark structures that we're seeing here. Okay, so and you might be able to do it with ultrasonics, because remember what I showed you with the Suhas Ralkar. I mean, this is ultrasonics and discharge, or sound and discharge, 300 kilohertz pulses of 200 volts, and you know, you're getting a 94.5% silver. So I would view that this has come from the nickel, and it's I would hazard a guess that if you start with nickel, you could start with copper, and maybe that would be fast as well. You often find copper and nickel, copper, silver, and gold mixed together. They like to be together. Certainly, my ring from Alaska was silver and gold. And there's this theory, as I said to you in the previous presentation, where you take the nucleus of the atom and you layer a whole new skin around it. It's a bit like the moon model of the atom, and you layer a whole skin around it, and you end up by moving down the table rather than adding a proton and moving across. And so it could be that what's going on here is the nickel is either jumping across to copper and then down to silver, or is the nickel is dropping down to palladium and then across to silver. But I think that since we saw this near pure nickel structure in a nickel sulfate solution, that this could have been synthesized in the coherent structure, and this might be the better way to do it, to have a nickel sulfate rather than try using nickel foil. But I think if you used either, you'd probably end up by producing silver, and maybe if you pushed it harder, you would end up producing gold, which we did here. In fact, you can see the path, can't you? In fact, between these two things, you can see the path. We've already done it, haven't we? We don't need to think about it again. Look, so you've got nickel, and we produce silver. And in this data here, in where the discharge deposit occurred, this blob here, we have palladium and gold, okay? So I think the nickel has gone down to palladium and produced the silver, and once it's at the silver, it drops down the table and synthesizes your gold. So there you go. There you go. That's it. That's your transmutation there. All right. So, okay, I'm going to look at your comments here. I'm going to work from the bottom up, sorry. So, Osiander Kun, so basically you would be using calcium carbonate as the enrichment element to make Fukushima cleaning process more economically attractive and also quicker. Been hearing most of the presentation. Okay, so essentially, yes. But calcium carbonate is known to produce limelight. Limelight, we know, is producing a temperature of over 2,000, 2,200, maybe as high as 2,567. 2,570 is the melting point, I think, of calcium carbonate. So we know that there's a large chance of producing cold neutrinos that will stimulate the transmutation process. But also, I believe with all of that kind of light going on, you've got a great scenario to energize the coherent matter process and drive that very quickly. It certainly looks really, really very, very, how should we put this, good at doing it. It has the carbon already in there to provide the CNO cycle, and it looks like it's doing the CNO cycle because you see that carbon going up and down. You see the synthesis of the nitrogen. It shouldn't be there. Yes, there's nitrogen in the air. I know there's nitrogen in the air when we exposed it to it. So it could be capturing nitrogen out of the air. I've told how nitrogen, I believe, is a fuel for LENA. And in fact, if you imagine the coherent matter is there and it's ionizing nitrogen, which become positive, get attracted to the negative structure of the ball lightning, that then becomes fuel and then drops into the the CNO cycle. So it's feeding itself with nitrogen from the environment. And I've argued that that is why you see 2 nitrogens synthesizing silicon and 2 silicons, or silicon, whatever. I've done that with the spectrum from ball lightning. So I believe that a ball lightning forming in the air produces silicon. You got the CNO cycle. Anyway, the point is it's producing spectrum from silicon and calcium and iron, and I believe these are all synthesized from the ball lightning. So the ball lightning can pull that material in, but the level of coherence that you're getting going on, it would appear in these structures which are blowing out is synthesizing the silver. And maybe you could push it further, I don't know, but I think probably the sound method with the electrical discharge here certainly produced silver and gold and palladium, and in the case of what we did, it was not so conclusive with the work that we did here. But we found silver in several different samples, but at a low rate. But you have to bear in mind that this was only running for tens of seconds. I mean, I don't even think it was running more than minute, maybe a minute and a half, maybe 3 minutes to produce this. So because this is so quick, anyone that had access to an SEM could run through many cycles, and probably I would choose to run this experiment relatively quickly with nickel sulfate, but I'm going to give someone else a chance to do it before me. There you go. I'm going to have another session in October on the SEM, and if no one's done it by then, I will do those experiments, probably do the whole thing. I'd like to do an experiment where we are filming the process end to end, so you actually see the whole experiment on a continual stream, a bit like I did with the testing with the Mars gas. So it's completely unbroken stream with all of the warts and all. But it would be great to be able to do that, maybe run the experiment. If you could synthesize palladium in gold, I mean, that would just freak them out. But you don't have to coat it with gold because it's already aluminium. So yeah, happy days. So Martin Lammers dropping in late, so I might have missed essential info. I heard nitrogen from CNO cycle. The experiment was in air, right? Yes, I know. Of course, nitrogen come from there. So it could be capturing the nitrogen in from the air. I've already argued that nitrogen, in my view, is a principal fuel in LENA, in ball lightning rather. So. But yeah, you can take the carbon and go through the CNO cycle, and it produces, as I showed in this thing here, you get nitrogen synthesized. You get nitrogen 13, which decays. That will not exist. You get nitrogen 14, which can be captured from the air. So if you're working in air, you can not only synthesize nitrogen, but you can also synthesize carbon. So the carbon can be produced from the nitrogen that you're grabbing from the air. But as it's actually in this sample that's been looked at, I believe the nitrogen is actually captured in there in some way or form. And so you're actually reading that nitrogen signal when you are doing the EDX analysis. And so it could be just eating nitrogen from the air and synthesizing. And I imagine if you ran this, the carbon and nitrogen would go up and down and up and down. You might just get a build-up of carbon, and I think the oxygen would be consumed until it would reach an equilibrium with the oxygen that is being consumed by the carbon and the oxygen that may or may not be captured from the air. But regardless, when you're using H2O, and you may not. Maybe this won't work unless you have the air, and you might need the nitrogen. But if you start with carbon, you're going to get the nitrogen anyway from the carbon that's in the CaCO3. So whichever way you're looking at it, you're going to get the transmutations that you need, in my view. And you can see how the carbon gets consumed here, and it's kind of going up and down. And the oxygen obviously gets clearly consumed. And the calcium's actually kind of like. It's kind of going down. It's progressing towards the heavier element. So I think you would get more and more silver as this went on. So I'm thinking that Amarza got silver from calcium chloride with his vibrator system, also from cesium. Well, he might well have got it from calcium because, as I said, You take the double calcium goes to zirconium, and then you just add carbon to zirconium, and you get palladium, and then you got hydrogen in the water, and so there you go. But when you get the coherent matter process, it depends on what you start with. Will it will help you move in a direction, either up or down the table. Okay. Yeah, so the Blaster Labs, you're talking about the bacteria. Well, the bacteria, all life uses coherent nuclear transmutation, in my view. I think the two most extreme examples of that I would give you are one, spontaneous human combustion, and the other one is when you get these monks and they go off into the desert and they go off into some cave and they just drink water and eat pine needles, and their body switches to a mode where they are burning nuclear energy. And they're taking water and pine needles. The pine needles have got carbon-14 in it and potassium 40, so there's all the nuclear energy you need, and the water is the other bit you need. Done. Spontaneous human combustion is a coherent process through the entire body where all your mitochondria trigger at the same time a coherent nuclear process that's either causing carbon-14 to decay or potassium-40, and you burn from the inside. And because of the way that it's a cold nuclear process, you don't burn things around it. It's not like it's a coherent nuclear process. So the stuff looks burnt, or even disappears. But it doesn't even burn things that are almost directly in contact with it because they're not coherent. Just like you saw the copper in Henk's reactor, and it's cut like a laser, like the 10 yen coin. It's cut like a laser. If you are in the coherent zone, completely you are vaporized. If you're outside of the coherent zone, you're basically not affected whatsoever. This is what you observe in spontaneous human combustion. And so when you understand this process, so much of the mysteries of life become really rather trivial to explain. Yeah, so Wim Hof is another person that's able, I believe, to get his body into a coherent matter state such that he's controlling, not too much because he doesn't want to do SHC, but he's controlling enough of his body so that within the parameter of his body, within that skin, he's able to generate all the energy that's necessary and it's literally a case of mind over matter. It's a spiritual. It's you having a much better control of your body, and it comes into the whole healing business and so on. But we can talk about that another time. But yeah. Yeah, I mean, this would not have been possible without Slobodan Stankovic, absolutely 100%. And all of the many researchers that have shared their data over the years. It needs, it needs to, you need to look at the pattern in the data. And, if I was coming at this 20 years ago, I'm not sure it would even be possible. I think with certain things published onto the internet and so forth, for instance, I didn't see the Solin pattern until August 22nd, 2000 and whenever it was, 20, last year. And that really lays down the whole process. But a bit like Matsumoto was really rather close. But the quality of the images weren't convincing to people. The concept wasn't believable. They all had their own idea. It was palladium and deuterium, and it did this, and you needed impurities, and you needed the loading levels, and blah, blah, blah. But Matsumoto changed throughout his learning. He started with one belief, and he went all the way down to something that fitted in with shoulders and fitted in with blah, blah, blah. And the same with Ken Shoulders' understanding evolved. My understanding has evolved immensely, and it could not have been possible without, in fact, with the community. If the community hadn't funded to go to the trips to see Suhas Ralkar, you would not have the data that I've shared with you tonight that forms an integral and a very important part of the puzzle. You know, it's it needs everything. It needs us to work together and to work coherently. And what you have now in this level of understanding of how HHO works, and the level of understanding with how ultrasonics works, you know, the star in the jar was 1920s, 30s or whatever, I don't know. And then it was Roger Stringham that really took that on board 30 years ago and worked and worked and worked. And he was using mostly the frequency that is in these $30 ultrasonic cleaning vessels, these 30, 40 kilohertz ultrasonics. And for most of his 30 years of transmuting matter, he was using those frequencies, which you can use for basically free. I mean, it's the opportunity now to accelerate this field is mind-boggling. It's literally mind-boggling. The Vega experiments are more challenging and obviously even more dangerous, I would say, than well-done HHO. And the results are not so predictable necessarily, but they've given us a spectacular insight into how a black evo will strike and it detonates and produces the EMP, how it consumes matter, what kind of matter it consumes, which is basically anything, especially if it's a metal, but mostly if it's a metal. And yeah, so it's only because of Henk and Dave and Suhas Ralkar and Slobodan Stankovic and people that are alive today and are actually doing experiments, and it takes grit, determination, personal sacrifice. But now you're getting to a point where you really actually have to not want to know to be able to do these experiments. You actually have to not want to care, you know, and the implications are just so phenomenal. For me, as someone who's been interested in energy and science and sustainability, you know, all of the nonsense that's going on around the world about what, you know, like rare earth elements and stuff. I mean, rare earth elements are great as a fuel for this because they've got a lot of alpha decay particles, and that's something that you can use to strange radiation to interact with. And I've argued that before. But you don't have to refine them. You just take the rock and you put the reactor in the middle, and you're going to get extra excess heat. And I will detail that all out in the future. But these things become trivial to understand, and it is not a surprise when you see the things in the data. And so there we go. Yeah, just study nature and let it show you what it is. Let it show you what it is. I believe that every time you put HHO of whatever variety, as long as it's half decent, and it's got a bit of the heavy stuff in there, and it interacts with calcium carbonate, you are going to see these same structures that we have been sharing today. I can pretty much guarantee that that will occur. And I can also pretty much guarantee that every time that you run a foil in an ultrasonic tank and you don't allow the foil to move away from whatever the resonance is that are set up, you will see transmutation in the center of these vortex pairs. You will, every time. This is total science. It is totally predictable. And you right now, you have the opportunity to be literally at the forefront of what will, I imagine, change humanity's prospects for our current biosphere and for management of and interaction with other potential places the way we could live. Elias, I believe there's an opportunity with the tritium water to produce some extremely valuable products. It's got buckets of neutrons that don't want to be next to one proton. They want to be in a much bigger environment where they don't feel so left out. Yeah, think of it like that. The neutrons, you know, they are something that likes to be partnered. They don't want to be, you know, three's company. You know, two's okay. That's a partnership, but that's as far as it wants to go. It doesn't really want to be in anything more than a partnership. But 3 is like pushing the limit. It doesn't want to be that 2 neutrons, 1 proton ratio. It doesn't want to do that. It's quite happy to join another nucleus where, you know, that nucleus like calcium 40, it can go 41, 40, all the way up to 48. It's quite happy to do that. The zirconium nucleus, you know, tin, obviously, most isotopes of any element. You know, there are elements out there that are very, very happy to say, come on in, neutron, you can join me. And it's you've got nature, it's wanting to reorganize things, but it's kind of like, it's kind of almost like people going to church and saying, I have all this excess that I don't need, but I do need this, right? And can we do some bartering so I don't have a lot of stuff I don't need and you don't have a lot of stuff you don't need, and we're all kind of like happier. It's kind of like that's what this is nature. It wants to make the environment for life. It wants to create all the elements when they're not there, if it's put under enough intense pressure. That is the creation process, but it'll also recreate. And this was observed by Solin. It was observed by Matsumoto. I'm sure it was observed by many, many people, many thousands, maybe millions of years ago, possibly billions. Okay, I'm just reading your comments. Thank you. Some fantastic comments, really. So, Anbeck, the cold neutrino condensate, in my view, is chi. It is chi energy, and humans can focus it as all life can. All life and things that want to create life, i.e. vortices and evos, they can cohere chi into matter, or use chi to convert one matter form to another, or destroy matter, or synthesize matter. Okay, sorry if I'm quiet. I'm just running through your comments. It's probably an all-day job in its own right. So the one warning that I will give anyone with any of these systems is that coherent matter, because it doesn't see normal matter in the same way that you or I do, like I can push my hand over here and I've got an electrostatic charge on here, an electrostatic charge on here on all the atoms, and it's able to push that matter over here. It might just go through, right? And it'll go through any containment. So I would be very cautious to push things very hard. And the quickest way anyone's going to kill themselves is with cavitation. Ultrasonics, when you have a fixed place for the focus of the resonance for the cohering process to take place, is going to build and build and build. And I believe that experiments along the lines of what we've been doing with Echo is exactly showing this process. So in the last presentation, I went through a series of these figures of eights, which you might like to call them yin-yangs, but anyway, they are building matter. But what I like about this experiment is that the foil eventually yields. And if you do get iron synthesized rapidly, because the coherence is very tight, it will rip the section out. And so it almost has a self-limiting factor involved with it. And this is something that did not exist in the aluminium foil and pressure drop hydrosonic pump type apparatus of Leclerc. And that, I think, maybe if they were exposed for about an hour, I think if they were exposed for 2 hours, they would have killed themselves. In the case of Shishkin, and I'm going to be translating a Shishkin paper because it's extremely important to understanding where the excess energy is coming from in a lot of these systems, I believe, and I think he's got that right. His reactor, he's calculated that the energy flux that he's already recorded coming out with X-rays in these string vortex solitons, these monopole like cold neutrino condensates that are carrying nucleons with them, regardless of what the cold neutrinos can do to your sugar molecules that bind your DNA together, which are comprised of 1 part in a trillion of the carbon atoms are carbon-14 and then can be converted into nitrogen with the interaction with the cold neutrinos. There is also the atoms that they collected on the way that they fire out when they dishevel, and they are literally like atomic nuclei bullets, which can go into your red blood cells and kill them immediately, and your white blood cells, and cause DNA damage within the white blood cells. And so he calculated that 1 hour next to his pump, his cavitator, would kill a normal human. And so when they run it, they're several rooms away behind some various barriers, and they operate it remotely. And so don't push this to the max. The ultrasonic with the aluminium, I think, it's good that those devices, the maximum you can run them for is 360, and when you run them, typically I should imagine that most of the aluminium will be torn to shreds, and so the bit where the coherence is occurring is torn off, and so you end up with a self-limiting system. But of course, those people that want to push it further could choose thicker aluminium, they could choose different materials and so forth, and that's when the science needs to come in, and it moves away from something that a 5-year-old could do safely in 20 minutes, including instruction time, to something where you don't want to be creating unpleasant. The purpose of what we're doing here is to try and create safe and de-radioactive process, not create lots of radioactive material. M3 SCAR1, I suggest, or MESCA1, or mescaline, maybe that's what that's meant to be. I welcome. I would really recommend you walk through this presentation. You've missed a lot. I'll run through it briefly at the end, which won't be too long away now. Is Solin patent on the download page? If you go to my monopole clutch video, I've got a rough translation and the original in the PDF that you can get from the monopole clutch presentation, and the link to that is in the video, that my 2019 Russian presentation, or 2020, maybe my 2020 Russian presentation. I'm going to be translating next week the 2002 paper, and I'm going to organize it so that the images that are being discussed will be in sequence, so it's much easier to follow. A lot of people can't read patents, and me included, when it's kind of like asking you to refer to image 30 and this particular thing, it just becomes so tedious, most people give up, including me. Anyway, great to have you here, Blues Doctor. And just to say that for those that have missed it, I think we've proved in the last 2 weeks that this likely is a coherent nuclear transmutation process. We have places where coherence must occur, leading to the synthesis of elements in progression, in concert with and in harmony with the level of destruction of the material. And that was what I was talking about with the ultra experiments. And there's a long history of why this should work and transmutation. And it's the fact that these elements like this is boron synthesized in here. And if you actually look at boron, it's quite a common element in the crust. And I will walk through the transmutation or production of boron there. But we've also got copper and calcium and so forth, and a good spread of elements on this structure, which is fused in. And for me, these are more important, where you have an agglomeration, which there doesn't seem to be any change. It's not like separate from it. It's actually part of the aluminium. And so I believe a coherent state arose here, and the nuclei within there were changing to and from each other and sharing nucleons and whatever in a way that is difficult to imagine. But the evidence is pointing in that direction. And in the presentation last week, I showed how I believe a coherent matter structure came out, and it was producing copper and zinc, but it was in a similar structure to this one. In fact, they're about the same size. In fact, I'll probably draw those up. So this one here is about 10 microns long. This one's about 10 microns long, and I guess it's about 4 microns wide, okay? And the structure we had from last week's presentation, I'll see if I can find it. I'll just bring up maybe the image, which is not that image. I think my next presentation, for a bit of fun, I just want to explain lightning from beginning to end and what I understand as the whole process, the coming down, the splitting up, the final charge that hits the ground, the bit that goes up, and all of these crenellated iron spheres, which I believe that are in the feelers, the ball lightning that makes the lightning track. I think I might do that just because I think it'd be a bit of fun for me. Okay, so not that. Or maybe it is that. No, is it? What am I looking for now? I'm looking for this one, yes. Okay. No, I don't want to look at it like that. In fact, I know what I'll do. I will try and drop this in to the presentation, so I can just have it alongside. Okay. So I this is quick and dirty, I'm sorry. So this is copper and nickel rich, copper and zinc rich, and it's from the aluminium foil, and it's like bursting through the side of a cone on aluminium. So I think this was a coherent matter thing that flew away from the cavitation and vortex bubble that is forming on the other side of this wall here. And this is your aluminium, and it's blending in. It's the blending in bit here, and this is almost like kind of attached, but it's not. This whole thing is essentially silver, but you can see that this is about maybe 4 microns diameter and about maybe 10 microns long, and this one is maybe, it could be up to 4 microns wide, and you don't know how much of this coherent matter structure is sitting through the back of here, so it could be an equivalent size structure, but this is basically 98 or 97% silver, and this is a large proportion of copper and zinc. But it then blends into the aluminium and carbon here mixture. So this is the kind of things that along with the diamond bullet that we observed, these are the kind of things that I don't want to see people finding in their bodies. And so this is why even I would always keep your distance from these experiments, whatever. But I think it's quite nice, really. I'm looking forward to a time when there's a lot of people sharing these kind of synthesized dead coherent matter traveling waves, as I Currently think they are, but I'm open to completely changing my view if I see something different that points in that direction. What force is causing the cavitation? It's a... I will show you. Hopefully I haven't got water in it. Okay. Okay, sorry. Yeah. It's a vivrial. Oh, there we go. It's a bit dusty. And it's not dusty inside, which is good. And so there's the chamber. And under here, there is a 43 kilohertz PZT. And then I use this. And you can go and look at the description of the experiment. And you put the foil on the underside of that. And you put the water in there. And you put it in there. And it holds itself in place. So it holds itself and the foil in place. And therefore it cannot move around. And you set your how many seconds you want to run your absolutely repeatable works every time experiment with your 0.5 of a dollar cent of working materials, and you run your experiment, and then you take it off to the SEM. It was kind of a bit of a serendipity. Alan Goldwater wanted to clean the indium foil. That was the starting material, for those that don't know the story, for the indium that I wanted to test in, that I had tested in Roy Shinamaza, Dr. Roy Shinamaza's vibrator system. And so we had a look at that, and we came to look at this material that he put in the cleaner for a few seconds, and he gave it to me. And on it, there were these... in fact, maybe I can dig up that image just now. Maybe I can, maybe I can't. Maybe I can't, maybe I can. Let me try over here. Oh, don't turn off. Maybe I can find that for you. And so he just gave me this. He said, right, okay, that's cleaned. And so I put it under the SEM. I said, Alan, you might want to look at this. He says, what? I said, it looks like it's got 3 resonant nodes here. And there's an explosion. In fact, I've since looked at it, and I might be wrong, but I'm not sure I am. I think you are seeing the paired vortex in that structure. But what you see, it's kind of like an explosion, and out of the side, there's this thing which kind of goes off, and it starts as indium, and then it goes through like carbon and oxygen and then silicon. And of course, if you get carbon and oxygen, you fuse them and you end up with silicon. And I've actually got a line scan, and the silicon's right at the end. So it's kind of like the ball lightning came out, and the coherent matter, and you've actually got the structure that it left behind, which is kind of what we are showing when we are seeing this. It's kind of the coherent matter came through, the most transmuted material is at the end, and then it falls back and blends into the substrate via carbon, and it tends to be a carbon tail on it. So it's just an utter pleasure. It's just an utter pleasure to be doing this work. Really, it is. And thanks for everyone's support and all the other researchers that are giving it a go, because it'd be nice when there's lots of people doing it. Okay, so where would it be? It would be in here. Yes, that's worked. Good. Don't go away. Indium thick. Is it that one? Okay. Yeah, so this is what I saw when I turned the SEM on. And when I was looking at this just a couple of days ago, it was kind of like, oh, hello. Does this look like we've got a vortex in here and a vortex in here? And maybe. It kind of looks twisty. Kind of looks twisty. So this was in an exact one of that Vivrial ultrasonic cleaner. And apparently you can get one of those, and found one for $30 on Amazon. I have no affiliation with Amazon. But you can see these are the resonant nodes, and I think each one of these is a pair. You have a pair, like I believe that this is a figure of 8 and this is the leader in, but you can see that almost this looks a bit similar to the structures that we saw on the Vega experiment. We have this kind of twisting and the twisting and the twisting. I wouldn't be surprised if it's just the same sort of vortical influence. So I've got this on different images here. This is rather beautiful, actually. Look at it. That's nice to share these things again. That's it. Looks like clay on this one. I like this one called the contrast. Here's another one from the top. So this is that one. So I think that probably you had one of the vortices here, one of the vortices here, but and you can see this kind of thing here going on. So maybe it moved slightly because this wasn't actually fixed in the tray, but it was clean for a very short period of time. When I say cleaned, it did this to it. So here's one of the ends, and you can see how the indium has this kind of fluidized carbon and silicon in this wavelet that's on here. Now, if you imagine that this was a piece of silicon that was like in the material as a contaminant, you wouldn't imagine that it would be flowing like this does. And again, you've got these crested waves here. It's not so clear there because it's charging. I'm going to see if I can find... where is it? Let me see if I can find the line scan. Oh yeah, here we go. Okay. All right, so this is quite a nice graphic. Okay, so what I've done is this is our figure of 8. Okay, and I identified this as something that's shooting out, okay, over here, this thing here. And so I zoomed into that, and this is what you see. You see this kind of thing shooting out, much like we were seeing on the other coherent matter traveling waves. And what's the size of this? It might be a similar size, actually. So what's the width of that? That's 30, so that must be like 10. So I would say that this is bigger actually here, but this bit here is about the same size as the other ones. So you can see how it blends. It's blending into the indium, and then it goes through this kind of darker area here, which means it's probably a lighter element, and then it comes up here, and this is bright, but it's bright because it's charging rather than it's bright because it's a heavy element. So what I did is I took a line scan along this section here, along this ejection, and so it's oriented the line scan round this way, and you can see that basically maybe you can't until I zoom in here, right? Okay, is that going to get in the way? Oh no, yes, it's going to. I can do it over there. Okay, so carbon, it starts at 60 and goes all the way up and all the way up to about this point on so where it's starting to come into this area, the carbon reaches its peak right here. Okay, I'll get rid of my mugshot. There we go. So the carbon is reaching its peak about here. There, it's about here, where you've got this darkest area. And at that time, the oxygen's growing. So carbon plus an alpha particle is oxygen. So the oxygen grows, and then in between these two, you've got a fusion between the two. Carbon and oxygen, fuse those two, and you get silicon. And silicon comes right out until you get onto this peak of this charged area up here, and then you drop between the gap and you've got another bit over here, and it comes up again. So in my view, what's happening here is some coherent matter is coming through here, and it's got indium down here, and it comes up here, and this is carbon, intense carbon here, the oxygen's going up, and then this is basically quartz. And it's blended in. Now, if it was an inclusion, one might imagine that the inclusion would just be a bit of quartz, like a crystal of quartz. It wouldn't blend into the other material, as we basically see when we look at this. this is blending into the other material, and what you get at the base of this before you hit the aluminium is something that's carbon rich, and this is blending into the copper rich and the zinc rich material. And I wish I had this sample under the microscope now, because I'd want to see if this comes down here and that this is silver, but maybe this bit is carbon rich on the end here, and maybe it's blending into the nickel. This is the nickel and sulfate. This is nickel sulfate crystals here, and this would be the nickel substrate. So it's whether it came in from behind or it just landed here. At this time, I just assumed this was synthesized in the pinch of the plasma or something. I didn't really know, because this was 2017, and then it dropped down onto the nickel foil. But having seen these things fly around on video, and as what I assume are these same things carrying the coherent matter, then you know, that's what I'm seeing here. Okay. Mescaline, any more development to the strange radiation spinner detector? Not that I'm aware of, although they've come back from their summer and they are doing their weekly presentations. I saw the last one on Wednesday last week, or this week. No, last week now for me. And they just reviewed ICCF 23 presentations on Wednesday, so maybe they'll start showing their work. I'm quite keen to share with them, because they've been trying to work out what the things causing strange radiation are now for the best part of 30 years, certainly 25 years, and definitely 20 years. So it would be nice to kind of fill them in where the community is on that. Okay, if anyone's got some specific questions, ask them now. Otherwise, I'm probably going to call it a morning. It's not a night anymore. It's a morning. Anyway, I've really enjoyed this work with Slobodan. And I kind of needed to dwell on this particular data until I kind of understood where it was going. But I think it is leveraging the CNO cycle, which is stellar synthesis, and so I think I'm probably just going to run through the slides quickly and just give an overview. Okay, so right, so this was looking at the before and after of calcium carbonate versus HHO, and the slide presentation is called Silver Linings. This was brought about by trying to find a better solution to those presented on the 12th of May 2020 to dealing with the triated water at Fukushima Daiichi, rather than the current Japanese plan, which is to build a tunnel, dilute the waste with seawater and dump it into the sea. I then went through my phenomenological hypothesis for what is causing what I believe is now best called coherent nuclear transmutation and ball lightning, and that the process likes to fit things into a small box. And I specified again that that small box obviously is not actually an width, height, depth. It's actually a sphere, and therefore an energetically advantageous product will be favoured. And that means something that fits into a small box will distort the physical vacuum less, and therefore you will get energy as a result from the less distortion of the physical vacuum. And then I noted here that calcium is very common synthesized, and also fermionic nuclei also, and the fact that calcium is the fifth most abundant element in the Earth's crust. And I have argued that the Earth's crust is the best representation over 4.5 billion years of what lightning and cavitation and things that produce coherent nuclear transmutation will cause, given sufficient time just churning it up, and the product is what you see is the crust. I then talked about magnetic field strengths from the messing around with someone's neurons at about 5 picoteslas, all the way up to 730 teslas for, in this data, the largest pulse field created in the lab, destroying the equipment but not in the lab. So you might think of this as a can crusher type or coin crusher type devices, or big versions of that. And then I reviewed quickly the key points from Lutz Jaetner's ICCF22 presentation, where the electric ring current produces up to 50 million teslas, and this ends up by producing a magnetic pressure inside the EVO of up to 2 times 10 to the 21 pascals. That's 5 orders of magnitude, i.e. 100,000 times higher magnetic pressure than in the solar core. And that this results in a density in the range of pulsars like a neutron star, so you can imagine that neutrons would be formed given half a chance, and that due to the intrinsic current of condensed plasmoids, they would exhibit pseudo-ferromagnetic behavior. And basically you can think of an EVO as an intense magnetic vice. It doesn't necessarily need to be intense, but if you cluster them and it gets to the point of self-coherence and self-compression, then it can go even further and do all the things that Matsumoto and Solin have identified in their respective works. Then how can they be stable? I talked about this and just showed this for the fact that it was published in October 23rd, 2007 by David Yerth, and why this is relevant is because this was in his work where he had spent 11 years using exotic vacuum objects to demonstrate remediation of radioactive waste by having an EVO generator. But I believe that the making coherent matter is almost more important by trying to achieve it in the simplest way possible, rather than specifically creating EVO type of coherent matter. Of course, they're all the same thing, but anyway. Proposal options, and then I went through the proposal again, and I talked about the fact that if you have tritium and you interact it with calcium, because calcium has many stable isotopes, and because it is very stable itself, and everything seems to fuse or fission to it in LENR, or you obviously you often get a lot of it produced, that it can absorb the tritium's extra neutrons in that isotope of hydrogen and produce other isotopes of calcium, moving up to the heavier isotopes of calcium all the way to calcium-48 by using tritium. And you'll notice that in these reactions where I've asked it to do hydrogen, deuterium and tritium, no hydrogen appears, and that's because these are all able to take a calcium isotope and go into a smaller box more than hydrogen can, and therefore they have a bigger energy yield. And so I believe that this will occur more likely, and therefore tritium will be more reactive in producing whatever this system produced than hydrogen or protium or light water or heavy water, normal heavy water, deuterium based heavy water, deuterium oxide. Okay. I then talked about the substrate, which is the target material, and the reason for choosing calcium carbonate was principally this calcium and the fact that it produces calcium oxide that produces limelight, and that should produce a temperature that's sufficient to produce cold neutrinos. And we demonstrated in our experiments that that is the case, and limelight, because of the historical record, we don't even need to put a thermometer on there. It is achieving higher temperatures than were achieved in Parkhomov's 225-day reactor, which would appear that it did a lot of transmutation of the tungsten, producing calcium, and that would have yielded a lot of the energy that was produced in that reactor, and therefore we should see a lot of cold neutrinos synthesized here also. That is the hypothesis. And the fact that we had some atomic hydrogen, and maybe more atomic hydrogen is made because the carbon takes away some of the oxygen from the oxyhydrogen gas and the Masing process. And we talked about the coherence process, and we talked about then all the well, I chose some examples of calcium being synthesized, and the first one that I saw was in what I now understand this triangle to be this significant structure in well, I saw it was significant back then, but anyway, the point is we've now got a lot of evidence of the same kind of structure forming. But anyway, there was only copper and oxygen in the substrate, but in the flux loop, a slug, there is the synthesis of carbon and calcium. And in this flux loop here, which is just another example, we saw this build up under the SEM, and these were these crystals which had calcium and carbon synthesized, where you had silicon dioxide in the quartz, which is here, and you had chrome, iron, and aluminium in the Cantal Fe chromium aluminium FeCral heater wire. Then I showed that when you had a Mars gas touching onto a tungsten, that this synthesized calcium in every spot, plus a lot of other elements you would expect from the fission process. And that is the same when you see these kind of things, which you also see on samples that have been retrieved from the event. You see these spheres, and on the spheres, when you look at them under the SEM, these are the sort of dead coherent matter or exotic vacuum objects that have burrowed around under the surface. You see all the kind of elements you would expect, but also in every sample you see calcium. You can see 14% here, where the tungsten is all the way down to 2% here. Now, if you do the reaction tables, that you are synthesizing mostly heavy isotopes of calcium, and so I explained that. And also in nanospire, Leclerc's calcium, zirconium, silver. And in Adamenko, you've got calcium, zirconium, silver. And then I talked about Solin's patents, and he's producing calcium and so forth. And then in Skiv, he's producing calcium and calcium from exploding titanium foils. And then in transmutation of tungsten with Simon Brink, where he's effectively creating HHO, he's producing calcium and zirconium. And then I looked at the original material, and you basically have carbon, calcium, and oxygen, and in two sample areas. And this is the gold coating that we had to put on, because this is a chargeable substance, and we got our ratios over there. And in the material that was produced, we had these quantum coherent nuclear reactor signature of these radial waves with waves on the waves going at 90 degrees perpendicular to the wave front. And this is all described in the Solin patents as the signature of a coherent nuclear point. And we found that on the sample, which was not part of this structure, which was coated by gold in the same time, that it only contained carbon, calcium, and oxygen, like the starting material. But on these wave fronts and in the crack, we saw silver being synthesized, and we checked that the silver was not a crosstalk between two elements that had some sort of spectral overlap. And you got the primary lines at 2.978 and 2.984, and then another one at 3.15, and both of them are clearly represented on this. So it looks like we're definitely producing silver. And then we showed that making silver in 2009 was observed by 5 labs out of 16 by George Miley when he did a survey in 2009. And I argued that this is probably because many of these people were using palladium and they were using deuterium, and there's a known reaction that takes one of the isotopes from palladium through to silver. And I discussed that with Mike McCoubry in my question to him at Colorado when he said, "Oh, we're getting lots of silver." And I said, "Well, okay, so it's just this reaction." But anyway, yeah. So and this was making silver with Ken shoulders, and this was presented in a poster at ICCF 10 using nickel in an aluminium oxide reactor and EVOs, exotic vacuum objects. He's synthesizing calcium and he's synthesizing silver. This was making silver, which I've just been talking about, and this again was using nickel, sulfate and water, and I walked through that in great detail. The first time I shared this was in Copenhagen in 2017, shortly after doing the test, and this is 94.5% and nickel. And so we discussed how if we use nickel sulfate in our cavitator in the ultra experiments, we might produce a lot more silver. And this was the actual device used. This is the foil produced that was analyzed, and this is the device, and this is a nickel, and they are discharges of 200 volts at 300 kilohertz. And on the foil produced, some of the foil produced, we found spots which look like this, which were agglomerations. And I imagine that these are more spherical clusters, and you can see these geometric shapes you see in kind of like in Matsumoto's work. But anyway, on the outside, a part of this was this structure here. And so we looked at what that was, and it had 31.9% of gold and 7.2% of palladium in this part, which was captured onto the main part of the center of the top of this structure. And so I argued that if we look at the periodic table, that if you start with nickel, you do a kind of like, I think it's a moon model, but anyway, you wrap a load of nucleons around a nickel and you go to palladium, then you just add a proton and you go across to silver. Or you take nickel and go across to copper with a proton, and then you wrap a load of nucleons around that and you go down to silver. And once you've got to silver, you wrap a load of nucleons around that and you end up with gold. And so, but it's a very, very basic, kind of very rough way of thinking about it. But certainly we showed other data from you've got the palladium here and the gold here, and in the same experiment you've got the silver produced here. So in this instance, I think that we are where are we? We are going from the nickel sulfate down to palladium, across to silver, and then down to gold. So I think that people in a cavitation system might get to gold by using nickel sulfate in their cavitator, and that might be a good fast way to get there. And then we showed how in the aluminium foil, where we've got no nickel sulfate, we synthesized some copper, and in that case we had some silver produced there. So it might be that in this case we're synthesizing the copper first, and then it's going to the silver that way. But it's very low concentrations of the silver, almost not worth talking about. It's only 0.81% by weight in this little spot here, so it's basically useless. But this only ran for seconds. So and you're asking it to cohere the matter here, and in this case I believe it was cohering in the actual solution. So maybe thinking about different approaches. Then I said that silver, because it's along with my phenomenological model, that silver actually has two fermionic nuclei, and since I believe the EVO can strip all of the electrons off a nuclei, then you end up with nuclei, if they're synthesized within the coherent matter state, if they are fermionic and the pressure's very high, it'll spit out those nuclei. So you might get synthesis of silver preferentially over and above, given the various scenarios which are to be determined. But they get spat out like the nickel 61 and the lead 207 in the Hutchison sample 18 coral twist. And so this might be the same thing going on, just like tritium is spat out because it's a fermionic nuclei, and also protium as well. They're kind of like balancing those ones. Anyway. And then I talked about how we could get to silver just by looking at the protons. So 2 carbons and an oxygen goes to calcium, 2 calciums go to zirconium, carbon plus zirconium goes to palladium, and then a proton and palladium goes to silver. So what have we got? We've got carbon, oxygen, and calcium in our calcium carbonate, and in our HHO we've got HH and O. So you have everything you need to get to silver just looking at the protons. But if you look through, it's okay when you're looking at this DPD 105 to 107. This is a reaction that I'm saying that you would see in normal cold fusion. However, these proton and palladium reactions go to the two isotopes of silver. You need 106 and 108. And this is all possible with what we have, as long as we have palladium. Well, how do we get to palladium? Well, if you take isotopes of zirconium and add a carbon to it, you can get to isotopes of palladium. You want 108 and 106. And so you get 108 from carbon-12 and zirconium-96, and 106 from carbon-12 and zirconium-94. So you want zirconium-94 and zirconium-96, which respectively are... zirconium-94 is 17 point something % of normal zirconium, and 96 is 2.8. So there's what's that, like 20% roughly? Yeah, roughly 20.2%. That might be your upper limit, but anyway, how do we get to these heavy isotopes of zirconium? Well, it's hard, because we can get with heavy isotopes of calcium, we can only get to lighter isotopes of zirconium. So we need more neutrons. How can we get more neutrons by doing this? Well, if you actually go back to where we were at the beginning, maybe if I play and do it like this. Where are we? Anyway, it's not in there. It's not in there, is it? Firstly, we can synthesize neutrons from cold neutrinos, but also we have a path using the CNO process, which is stellar synthesis, and this produces at 2 stages in the decay of 13 nitrogen and 15 oxygen a positron. The positron's in the coherent matter system. This will yield, may interact with electrons that are part of a neutron, annihilating them, producing 2 5 electron volt photons, which get captured by the coherent matter of the coherent matter condensate, produce extra neutrons, and the neutrons can go on and produce heavier isotopes of the calcium and heavier isotopes of the zirconium. And as you go round in this process, we observed in the an element analysis of these samples on this part of the material that, if it's going to show me here, you start off with no nitrogen, but you get nitrogen. And where would the nitrogen be coming from? Well, either it's captured from the air, in which case that can go through the NO cycle to carbon and produce carbon, which means you get a stable up and down of the carbon production. So the carbon doesn't disappear entirely, but you get nitrogen in the actual material that you are analyzing here. And so that nitrogen is showing, I believe, that you're going through this stellar process, and you are producing a lot of energy in the process of doing this, and you're absorbing a lot of atomic hydrogen, which we're getting from our HHO, and we are then producing stable 14 nitrogen and stable 15 nitrogen that's in the mix of the material. And this ends up with some nitrogen in those sample areas. The oxygen is absorbed because we've shown that needs to be part of the process in the synthesis process. Oxygen, of course, can, if you do your reactions down here, O is 4 alpha, O2 is 8 alpha, 10 O2 equals 80 alpha equals 2 calcium. So you can actually, and you're also getting helium synthesized here. So you would end up with a kind of varying amount of calcium here. The oxygen gets eaten, and you get this progression of production of silver. And you would probably end up getting to a limit in the silver, and then maybe the silver would progress onto something else when the overall system finds that it can't gain more energy by crushing it in this way. It might find that it has to crush, if it's overdriven, the silver onto other elements that may or may not be elements that you would want. I mean, if you went down from gold, you're going somewhere where you don't probably want to be. And I think that was probably about that, really. This was, I believe what we've done is we've shown that we see something that looks like a coherent nuclear transmutation process. The physical evidence looks exactly like that shared in 1992 by Solin. The elemental transmutations are supportable by the amount of elements in the observed mass post exposure to HHO. There are all of the elements required to do the transmutation, whether you're looking at Bolotov's claims in his patent from 2001, is it 2001? Whenever, 2002, 2001, which is about to expire in November, and all the other people that observed the production of silver, including ourselves most recently this month. This month, I think, yeah, this month, and in ultrasonic tanks. And so I think we have a solution that is proving that it must be absorbing a lot of neutrons. Tritium will want to give its neutrons to calcium. I believe that it will produce silver faster, and even deuterons would produce silver faster. And we have a system that, as I said earlier, gets rid of the tritium, produces something of value, and may actually produce energy in the process. And if it's going to cost them 30 million to dump this into the sea, with all the potential risks that entails, there's got to be someone out there that has 30 million that might want to buy the waste off them and make something of more value. I don't know. And if it pushes it, you can go from silver and go down to gold, even better. You know, there we go. But I'm not sure it would be a lot. And I described a process where you might be able to refine it, but it's early doors on that. So there we go. Okay, so I'll see if you've got any questions, and then I will say good night. Slobodan Stankovic asks, Bob, what would you need the next step for Fukushima? Do we need to get in touch with them? I would like to verify this data. I would also like to do a test with deuterium oxide, probably a lot more than I get the 5 mil that I already gave to you. And that's going to be expensive. And so I would like to see if the concentration is more, or the outcome is different in some way. And that will give us an indication as to how the extra neutrons are playing a role. And so once we've done that, I think we can work through Iwamura. I think we can work through Francesco Celani. I think, you know, we will try every angle. What's his name? Vysotsky. And directly, I think even walking into the embassies and just say, look, you know, you really want to sort this out, because of course we would like to be able to go to Japan. That would be great. Amasa can verify this himself in situ. I can actually send him some of the calcium carbonate that we used, and so he could verify it. He just needs to get access to a service to hire and just check that they are observing the same structures that we are observing here. And from my point of view, I want to translate the Solin 2002 patent because the structures are so extremely the same, and he goes into the quantum mechanical kind of explanations for why you get what you're seeing here, these radial waves and then the perpendicular waves on each of the waves, and so forth. And I've shown in Hutchison samples how you can have these wave functions of different elements overlapping and mixing. And I think a similar thing is going on here. And I think it's just a beautiful thing to see what is the signature. And this is what he says. You don't need to do elemental analysis to a certain degree, because you physically see the signature of the quantum coherent nuclear process. You actually physically see it. So and it's so big in the case of things like the Lion reactor and stuff. You can see it with the basic microscopes, even to a degree. Just phone level microscopy can do it with the basic, let's say, Nerugo lens. Yeah, I think we'll send the data, but what I want to do is, no one's going to listen through 20 hours of videos, so I've got to nail it to a presentation, and in part, why I make you suffer through my thinking is an analysis, is that by doing that and disciplining, and with your feedback saying, like, I don't understand this or I do understand that and blah blah blah, I can learn what is important for most people to get the most important facts as quick as possible, and then I can pare that down to the core data. And then if there are interested people, you've got to have a buy-in with people who are already sold on something. They've got to have a reason that's motivational enough and emotional enough for them to both, and different stakeholders. So you've got the fishermen, you've got the people in the prefecture, you've got people in the government, people that work at TEPCO, you've got potential investors that might want to see this because they might actually earn money by dealing with the waste rather than it being a burden. It becomes an asset rather than a liability. You want to make it an asset, and so you've got to get the whole package of the story together, because my experience is if you go to a person and you have a half-baked story and they can't get it, they've got very little time. You've got to think of it like an elevator pitch. You've got 5 minutes to sell the entire thing, and if they don't understand it in 5 minutes and it doesn't float their boat in 5 minutes, then that's it. They've given you your 5 minutes. That's their very expensive 5 minutes that they've spent listening to you for 5 minutes, and they don't want to have another 5 minutes where you try again. They don't want that. They want it. You've got to be right first time, and so that's what we need to do. And anyone can help hone this down. I'm not a physics teacher, but I studied a lot of physics. I don't like equations, mostly because no one else likes to hear them. So I like to see what's going on, and it to be repeatable and ideally easy. And then I like the science to match up with something real that exists in nature naturally. Okay, so I'm going to say goodnight. Thank you very much for your time. Dobro noc, buenas noches, bonne nuit, dobre den, dobre. I'm too tired. So I'll see you. And please, if you have comments that include links, put them in remoteview.icu, because you can include links in there. If you want to comment generally and you want it to persist, if YouTube ever gets taken down, all of the comments die with it. So really, I would prefer, I can upload the video into Remote View through a different platform if YouTube goes down, but I can't, there's no easy way to capture all the comments and transfer those across. So and also you can have a better dialogue in there generally. So just that's my request, is if people want to ask questions, rather than putting it in 2 places and I have to track between the 2 and then half of them get lost because someone's put a link in there, just put it in remote view. So on that note, thank you very much for your time, and I will see you in the next video. Bye for now.